The scientific revolution starts now.
This is the Science Joy Podcast.
Let us see in the dark.
I'm Sean Raymond. I'm an astronomer in Bordeaux. I officially work at the Bordeaux Astrophysical Laboratory in Bordeaux in France. And my research, so the kind of research I do is mostly about planets. It's mostly about how planets form, like how the solar system came to look like it does today. And also, not just the solar system and the planets, but also the small things in the solar system that are kind of leftovers of planet formation, like asteroids and comets. Also, interstellar objects, which are leftovers of the formation of other planetary systems. And also other planetary systems themselves, like exoplanets, finding them, trying to learn stuff about them, how they form, and how their orbits change in time, what they're made of, all these kind of things.
Yeah,
Free floating planets too, which are planets that don't have stars at all.
Yeah, I was gonna say this feeds into a really interesting, I feel like, opening window into how solar systems change over time, because when I was taking intro astronomy, it seemed like the idea was basically the solar systems form exactly as they are and they sort of stay that way forever. But it seems like that picture's I actually feel like astronomy or planetary science is one of the fastest moving fields in this way, and that the paradigms are changing so rapidly. It's kind of really exciting. But it does seem like people have had a resistance to the idea that things could change, like this anti-catastrophism kind of mentality, which is understandable on one hand, but it might be clouding our vision on the other hand. I don't know.
Yeah, this is, I think, what's been super useful for this kind of thinking is comparing exoplanet systems with the solar system. And so before the first exoplanet system, at least that we attribute to now, is found in 1995. And over the following decade or so, there were another 100 or more that were found. And so you kind of got to get this kind of weird picture of what other planetary systems look like. And comparing those with our own solar system, I think, opened a lot of windows in terms of what might happen to shape these things. And so one of the very first attributed exoplanet that was found, 51 Pegasi, that won the Nobel Prize for Michel Mayor and Didier Queloz. That's a hot Jupiter, so a big Jupiter mass thing right next to its star. And so no one really expected that. There were a few theories out there that could already explain it at the time, but no one took them seriously. Right? And most of the planet hunters were looking for planets like Jupiter on orbits like Jupiter's. And some planet hunters actually had hot Jupiters in their data in the bag, but they hadn't thought to really look for this kind of signal. And so it was people who were coming actually from a different field, were coming from binary stars, where there are very short orbits, that found the first planet around another star, instead of someone who was coming at it from the angle of looking for planets like our own solar systems. And so one of the first things that was found after these hot Jupiters were that a lot of kind of Jupiter mass planets had very eccentric orbits, so very stretched out orbits. They weren't circles; they were ellipses, like all orbits are, but kind of very stretched out ones. And this is held to the present day. Most Jupiters around other stars don't have orbits like our Jupiters, which is not quite a perfect circle, but kind of a circle. It's only has an eccentricity of 5%, so its orbit's mostly a circle. But a lot of these Jupiters around other stars had these really stretched out orbits. And so one of the kind of first puzzles, or maybe the first two puzzles in terms of the orbital dynamics of exoplanets, were, what's up with these hot Jupiters? Why are their orbits so small? And what's up with these other Jupiters? Why are their orbits so stretched out? And so people thought about these things a lot. This was a big kind of key areas of research early on. And for explaining why the orbits of hot Jupiters are so small, kind of the thinking then, which is held up to a decent amount now, is that most of those planets probably form much farther away from their stars, and then their orbits shrink. And why do they shrink? They shrink because of gravitational interactions between the gas disk that they formed in, that has a lot more mass than the planets themselves, and the planets. And they end up launching these spiral density waves and doing other cool things within the gas that change the planet's orbit, usually causing it to shrink, and can produce hot Jupiters. The one that has more of a connection to the solar system, which is where I'm getting in this very long-winded answer, is the ones with very stretched out orbits. And very quickly, within I forget within like 6 months or something like that, of very eccentric orbits being found, people came up with the idea that the planets that we're seeing on these stretched out orbits are the survivors of some dynamical event that really shook up their system.
Mm.
And what that dynamical event is thought to have been is what's called an instability, meaning that we see, for example, in some systems we only see one planet on a very stretched out orbit. That stretched out orbit means that it formed with at least one or maybe even two other planets on much more circular orbits, because the disks that we see that form planets are pretty circular. But then something happened to change orbit. So what changed is we can see in computer simulations that over time, systems with many planets, they kind of gravitationally jostle each other around, slowly kind of change the shapes of their orbits just a little bit until their orbits cross. And you might think, oh, if two orbits cross, that means they might collide. And that's true in some realms. For the realm of really massive planets like gas giants, usually their gravity is so strong that when they come anywhere close to each other, they can kind of gravitationally slingshot each other all over the place. And doing this long enough is this kind of chaotic sort of process where what happens in the end is there'll be a really close encounter. Usually one or more planets will get launched into interstellar space.
Whoa.
And the survivors will have these stretched out orbits. And so the interstellar space ones connect with the idea of free-floating planets that we can talk about later if you'd like. And the survivors have these stretched out orbits like what we see. And so that was thought of for for exoplanets. And it was only several years later, it was only in 2005, that a really big model came out for the solar system trying to explain that the solar system's giant planets also had undergone an instability. Not a really dramatic one like exoplanets, but still a pretty big one. And that really changed kind of that series of papers about the instability in the solar system really changed how we think of the solar system. Before that, there were always crazy ideas here and there. But most of them thought, planets formed, let's explain how the planets formed, because they were, basically how they are now when they formed. And after that, people kind of allowed themselves to go to that weirder place in their minds of maybe things were very different and there's something changed in between. And so this instability idea is kind of a key one. Sorry.
Now, do these planets that get launched off ever end up in somebody else's house? Like, do they ever join on to other solar systems, or is it just a big like graveyard of lost planets in
That's a
between
good question.
stars?
So yes, they can go near other stars. So we had the example in the solar system of a couple objects passing through the solar system in the past couple of years. Famously Oumuamua and Borisov. There's two known kind of asteroid-sized things that pass through the solar system. But where do these come from? They come from some large population of small bodies that lives between the stars. And those are the small ones. And there's always a lot more of the small ones. And there's always bigger ones in there too. And the biggest ones that would be out there, big ones out there, would be free-floating Neptunes or Jupiters or Saturns, or even more massive than Jupiters. And so you might think, well, would those ever pass through another solar system? And the answer is, yeah, why not? So let's do the math. I can do the math in my head because I've been looking at this for other stars passing close to the solar system. It's a project I worked on recently. So there's a 1% chance every billion years that a star will pass within 100 astronomical units of the sun.
Whoa.
So an astronomical unit is the Earth-Sun distance. So there's a 1% chance every billion years that that'll happen. The exact abundance of free-floating planets is not that well known. It's something, I think the upper limit is something like 1 per 5 stars, something like that. And so that means every billion years.
But it's pretty hard to see them, right? Like you're only going to see the really big warm ones or something, right? It's very difficult to see. Yeah, so it's hard to tell.
You can't see any of them directly because they're so cold and faint. The way that we detect them is by generally by microlensing. So by looking at background stars and seeing the gravitational signal, if a massive object of any kind passes in between, and the duration of the signal, the little blip you get from basically the gravitational microlensing, tells you something about the mass. It's tricky. It's a little hard to disentangle, but they've measured some of these really well. Sometimes you can measure them directly. You can see them directly if they're very young, because then they have their own internal heat. And so to do that, you look in places where young stars are born, and you look for things that are so faint that they can't actually be stars anymore. And so new things like the JWST, the James Webb Space Telescope, found 500 or 600 of these things in the Orion Nebula Cluster a couple months ago.
Some of them are orbiting each other. It's very bizarre.
This is a weird mystery right now, is that some of them seem to be binaries. So something like 10% of them are binaries, which is very weird, that no one expected. And whether that really holds up remains to be seen. But it's a very interesting. It's one of these kind of cool mysteries that someone finds something and says, "Wow, where did that come from?" So
Yeah,
now we
maybe
can figure that.
I want to come back to those, but I didn't mean to sidetrack you. So there's a 1% chance that
Every billion years, we have a star that comes within 100 AU of the sun. And you're saying that there's one rogue planet for every 5 stars.
Yeah, something like that. I think that's the upper limit. It might be.
I've seen estimates that are like 10,000 of them per star.
So it depends on what masses you're talking about.
Mm.
So for big things that are, what we really think of as planets, like Jupiters and Saturns, right? There was a paper about 10 years ago claiming that those free-floating Jupiters were more abundant than stars in the galaxy, that there were 2 or 3 of them for every main sequence star. And a friend of mine, Dimitri Veres, and I, we got together and we decided we were going to figure this out. And within like half an hour, we determined conclusively that we could not explain where they come from, at least not with the kind of idea we were thinking about. And so if those planets come from instabilities, or if they form around stars, then 1 or 2 planets get chucked out, and those are the floating planets we see. It's impossible to explain it that way, because there were too many, according to this one study. But a few years later, another study showed that study was wrong, way wrong, by about an order of magnitude. And so there, instead of being, a couple of these free-floating Jupiters per star, there's maybe one for every 5 or 10 stars. So to make the numbers easy, so say there's 1 for every 10 stars. So then instead of a 1% chance of one passing, within 100 AU of the sun every billion years, there'd be a 0.1%, so 1 in 1,000 chance of that happening. So, but it could happen, right? So,
and what would that look like?
What does that mean? We know like a couple thousand exoplanet systems. So free-floating planets have passed within 100 AU of at least a couple of those.
And what's 100? Can you give us a sense? That's like well beyond. That's like a few Jupiter radii away from us, right?
Oh yeah. So 100 AU. I'm using that as kind of a very rough limit for inside this distance of the sun. If something with enough mass comes there, something interesting might happen, right? It might or might not be destructive, but something interesting will happen. We would be able to detect that now with current telescopes. Probably not until recent history, but we could detect that. And so 100 AU, the orbit of the widest planet, Neptune, is 30 AU. So it's about 3 times that. So it's still pretty far away from the sun. But it includes, the area that's much closer in. Mm-hmm. And the way these things happen, it's kind of like a target, like a bullseye. So like you're playing darts, right? And so, what are the odds? If I'm saying the odds that a star comes within 100 AU is a certain number, right? Then what are the odds that it comes closer? So the orbit of Saturn, its orbital distance is about 10 AU. So imagine a Saturn, a free-floating Saturn flew 10 AU from the sun. That would be like, it would basically cross the orbit of the real Saturn. And it would probably cause something interesting to happen. It might disrupt the planet's orbits. If it's going fast enough, it might just zoom on by and do nothing. You don't know, right? But it would be dangerous. And so what are the odds of that? The odds of that are basically, if you look at a target, the odds of that depend on the kind of the surface area of the different circles. And so they scale with the distance between, basically the close approach distance squared. And so that means if there's a 1% chance of going within 100 AU, there's a 100 times smaller chance of going within 10 AU. That's
good.
I was going to say, so this is a statistical analysis of just, in general, given how many objects there are out there. But we do occasionally go through areas of increased object density, right? Isn't that
You mean like as the solar system makes its way around the galaxy?
yeah, like I feel like there's periodic moments in Earth's history which there was a lot of impacts, and the impacts seem to be because there's some kind of
Well,
debris fields that the solar system is crossing. And does that
I
not
think most
elevate
of
the
those
risk?
impact histories are attributed to the formation of the solar system. I guess from my basic
I
astronomy
remember
knowledge.
reading that the asteroid that killed the dinosaurs was one of those.
Oh, I see.
There's some debate about these points, but it's a good point. So as the sun goes around the galaxy, there are spiral arms that we kind of go through where the density of stuff is higher, and so then the rate of occurrence of the rate of things coming closer would go up and down depending exactly where you are in the galaxy. And so the numbers I was giving were kind of averaged over all that. But there are places where it would be a little higher and places where it would be lower. If you happen to be in a star like in the galactic center, then there'd be close passages of other stars all the time.
Pardon the interruption, dear listeners, but we must ask you for a favor. If you like what the Demystify Sci podcast does, consider coming over to our Patreon. It is at patreon.com/demystifysci, and there you can contribute a couple dollars a month to help us keep the ship running and allow us to continue our investigations into the most interesting ideas that are out there about nature, humans, history, the future, technology, economics, all of the things that we do on the podcast. In return for your donation, you get both of our episodes for the week early. You get to join our fantastic patron chat that meets weekly on Sunday mornings to talk about everything that is interesting in the world and the direction that the podcast should take. And you get to have the satisfaction of contributing to something that you think is important in the world. If you can't contribute right now, that is totally fine. We understand. I have been in that boat for many, many years. But what you can do without spending a single penny is come to our Discord, come to our Facebook, come to our Twitter, come to our Instagram, like, comment, and subscribe, because by helping us with the algorithm, you help us grow in a really super passive way. And if you've already joined the Patreon, just do all that other stuff too. For now, back to the conversation.
And this is something I've been thinking about calculating. So there will be tons more close approaches to the sun, but all the stars are moving way faster too. And so the actual strength of the perturbation, like how much a star messes up a planetary system, depends on how much the star really changes the gravity field. It's called like the impulse. And the impulse really depends very strongly on how fast the star is moving. And so if something whizzes by super fast, it has much less of an effect than if it goes kind of slower, because there's longer time to feel that gravity, basically. And in the galactic center, things are zooming super fast. So even though they're coming really close, I'm not sure how much stronger the perturbations are. That's something someone's probably figured out, but I don't know the answer.
Now, what would it take for one of these random planets to actually end up in a new orbit, like for it to join a solar system?
It's not easy to join us. This is one of those things that would be lovely to happen, because basically energetically, if it comes down to imagining, a star floating around and a planet floating around, and they're not gravitationally bound, and then they happen to pass by each other, and you're hoping that they'll capture. And so the only way for that to happen is for some of the orbital energy to go away, and some kind of dissipation of energy. That can happen if this planet that was coming to be captured had, say, it was a binary planet, actually, for that matter, and one component gets captured, the other one gets kicked out. That could work. Or if the planet passed really close to the star and got really deformed temporarily, and then there was enough friction inside it to dissipate some energy, that could result in capture. That kind of thing.
Is it not possible for something to be moving slow enough to just be kind of picked up? I mean, I know that things in motion tend to stay in motion, and so you have something that gets ejected. And is everything just moving so fast that it's impossible to have that gravitational interaction last for long enough that it gets captured without any of these massive deformations?
Maybe ends up in the outer, like in that Oort cloud region, and sort of stabilizes its speed out there, and then eventually kind of worms its way interior or something like that. I'm just throwing stuff at the wall. Sorry.
So what you're talking about? So yes, if there's a little bit of energy dissipation, then sure. So you can imagine. So if things are kind of zooming along in the galaxy, and a planet and a say a star with no planets and a free floating star, or a star with no planets and a free floating planet come from far, far away, and they happen to be coming close, and they're not moving that fast compared to each other. The romantic part of us wants them to just get together. But if you look from the point of view, say, look from the point of view of the star, the planet's coming from infinity, then it comes closer, and all this stuff. The simple gravity problem is time reversible, so there's no way to just capture it and grab it without losing some energy. So you have to lose some energy, and then you can grab it. Otherwise, you can't.
It is compelling.
Are there are?
Let me just jump in. There's a few little sneaky ways for this to happen.
Okay.
Yeah.
I knew you had
Gravity
something.
field is changing, then you can have it. But the standard simple problem doesn't work.
I'm just really surprised that you have to have a deformation or some kind of loss of energy in order for gravitational binding to occur. Because granted, my relationship to gravity extends to Newtonian mechanics, and that's about it. But what causes that? Like, if the force of attraction between two objects is like g(m1 m2) over r squared, where in that is deformation or the loss of energy in the initiation of the interaction?
Okay. So the deformation part would come from, imagine a star. So the star is here.
Sorry, the necessity for the deformation.
All right. Yeah. Okay. So why do we need that?
Yeah.
It's just a simple gravity thing. Basically, the relative energy of the two bodies, the binding energy, has to be below zero, basically, for them to stay bound. And if they come from infinity and they come together, they're still on what's called a parabolic or a hyperbolic orbit. So even if they approach not that fast, there's no way for them to stay together in the simple point mass Newtonian thing. So you gotta lose a tiny bit of energy, and then you can trap the planet in an Oort cloud or something like that.
It's like their inertia will just overcome the gravity that they sense there. There's some balance there, which I don't know the equation for, but.
And so I think something that's kind of deceptive is when I'm talking about the speeds, right? If they're really coming from really far away, they can never actually be really moving slowly next to each other, because they're speeding each other up from their mutual gravity because of that gm1 m2 over r squared. Right?
They're going to accelerate
So
as they get pulled towards
if they
each
were
other.
ever actually like really slow next to each other, then they would have already captured. There would already have been some kind of capture.
I see.
But starting from far away and then coming together, they're accelerating each other. Mainly the star would be accelerating the planet, but both of them. And so then they can't.
But like a planet with like some huge hefty moons or one of these binary Jupiter systems or something might satisfy the energy balance here.
Yeah, right. Because then you can just take a really big moon or a binary and check it out, and then you basically have an energy transfer where the one that survives can be captured.
I mean, could you chuck the planet out and keep the moon too?
Sure. Yeah. This is funny. This is not that different from something that I have been studying recently, which I can jump into if you're interested.
Please,
Yeah.
yeah.
So the reason that I knew that number of about a 1% chance of a star passing within 100 AU of the sun every billion years is because of a project I was doing. And the origin of this project was kind of funny. It was a science fiction author talked to a colleague of mine asking if it was possible for the Earth to ever become a free-floating planet, because she wanted to write a hard science fiction story where the Earth was a free-floating planet, not trapped around, not orbiting the sun anymore. And my friend, he said, well, maybe that's possible. But then he talked to me about it, and we were trying to figure out how that could happen or whether it could happen. And the idea we came up with was kind of, you can see where this is going, of maybe a star could fly by the solar system and disrupt the orbits of the planets such that Earth was launched out, ejected. And so for this project, I ran, 10,000 simulations of stars zooming by the solar system to see what would happen. And the numbers are kind of interesting because, Earth has about 1 billion years of life left. After that, the sun is going to be more than 10% brighter than it is now. And so by current estimates, we won't be able to have liquid water on the surface of the Earth anymore. And so in 1 billion years, we'll also have a 1% chance that a star will fly close enough that it might affect the orbits of the planets. And so this is why we were kind of motivated to look at this, in addition to the free-floating Earth part. And so we kind of shot all these stars past the solar system to see what would happen. And indeed, it is possible to liberate the Earth from the sun. The odds are not very high, but it's possible. There's certain
Liberate. That's a really funny word to use there. It's free.
Free the Earth from the tyranny of the sun.
Yeah, snowball Earth. Wow, that'd be crazy. I mean, is there? All right, let me take that one step further. In the possibility that it was liberated, would everything on Earth grind to a halt, or is it possible that it could make it to another home before, life was erased from the surface? Could it get like a nice ice sheet over it and have subsurface liquid and still survive how long would it take the Earth traveling at that speed to reach the closest star system? Just being super generous with let's say the next star system's perfectly aligned for whatever reason, and it just could somehow get in there. It lost its moon, let's say, or it had a bigger moon. I don't know. I'm really trying to make this happen. I'm just curious.
Yeah. So, all right. So a couple of things of that. So in terms of the Earth cooling off, this was calculated about 20 years ago. Someone figured out that for Earth to really properly, completely freeze over, it takes about 1 million years. And so until then, you can have, kind of a little ice on top with some patches of water here and there. So you can imagine you can find some way to have life persist. Then to get to the next star would take, I don't have the number off the top of my head. I think it's about 50,000 years, something like that.
Not much.
It depends on exactly how fast the speed of ejection is. But another possibility is that this star that passes through can actually capture the Earth, and Earth can just have a different, be under the tyranny of a different star.
That would really confuse those planetary scientists, I would imagine, if they're trying to make these like in situ models for planetary formation, and all of a sudden they've got this one that doesn't fit into the puzzle. Like, why is it? I guess it's just because it's so improbable that people generally don't consider captured planets when they look at the evolution of a solar system. It just seems like the timetables are just too big for people to even be bothered with it.
Yeah, I mean, there's all this circumstantial evidence against it being important in the solar system. Basically, when things are captured. So I was mentioning before that that a lot of these giant exoplanets have pretty eccentric orbits. Their orbits are pretty stretched out, and you can measure that. And so the typical number is something like their eccentricity. When you measure it, is just a measure of stretched outedness. Is like 25%. When planets are captured, or when anything is captured, it tends to have a kind of distribution that's called a thermal distribution, where the average or the median kind of eccentricity is about 70%. And so it's really, really stretched out orbits, basically, is what you end up with. And so if Earth is captured, it would end up on a really weird stretched out orbit around this other star. And so looking at it from the other point of view, the orbits in the solar system are not perfect circles, but they're pretty circular for the planets. And so it would be awfully strange if the solar system was captured. It doesn't fit the bill for how capture should happen. Maybe a few exoplanet systems with very high eccentricities were captured. That's possible. But
do those eccentricities iron out over time?
I was going to ask that too.
Do they what? Sorry.
Do they sort of even out over time? Is there any sense of that, or is it
does an eccentric orbit become more circular over time?
Yeah, or do you need some event to perturb it for it to become more circular,
or
is there no way back? Basically,
I'm beginning to understand during this conversation that my understanding of celestial mechanics is basically like zero ground.
Oh, sorry. Am I explaining things okay? Do you want me to?
No, you're explaining it really well. I'm realizing that I have super basic questions about it, and I really appreciate that you're here to explain.
Oh yeah, my pleasure. Yeah, so this is a good question. So once an orbit becomes eccentric, what can make it circular again? And so this is one of these things.
God's hands pushing it like on the wheel of clay.
Yeah, exactly. You just kind of stretch it out. You kind of erase the parts that are really far away, and you move them closer. But so in practice, there's two ways that this can happen that I'm aware of anyway. One of them that we actually have really good evidence happens quite a bit is if that orbit happens to take it really close to like a star. And in that case, you get the same kind of dissipation thing where the actual shape of the planet gets kind of squished around a bit, and it also excites these weird modes in the star. And what can happen is that in time, the shape of that orbit ends up becoming more circular. There's this dissipation of energy that leads to the orbit becoming more circular. But that's for orbits that are very close to stars. That might actually be relevant for hot Jupiters, but not for Jupiters. Right? For other planets, you can never kind of just get rid of an eccentric orbit, but it might not be the only orbit around the star. And so what matters in the end is not like one specific planet. The planets matter, but if you kind of zoom out, there's a whole collection of the orbits that are around a given star, and they all have different weights depending on the masses of each planet. Like for the solar system, Jupiter's gravity dominates by far all the other planets, and so Jupiter's orbit shifts a little bit here and there, but other planets' orbits shift a lot more. And so in time, there's kind of an exchange, kind of a dance between the shapes of planets' orbits and, on long, 10 or 100,000 year timescales. So in the solar system, this is called, I guess this translates to like Earth's orbital eccentricity varies between almost zero, so almost a perfect circle, and about 6%, which is still pretty close to a perfect circle, but not quite. And the same thing goes for other planets. Theirs also oscillate a little bit here and there. And you might think this doesn't really matter at all, but this is what's behind this and variations in the spin parameters, or what are behind long-term climate oscillations. It's called the Milankovitch cycles. And so our Milankovitch cycles, in some sense, are pretty wimpy, right? Because the oscillations are pretty small. You can easily imagine from these processes we're talking about that if you were to create your own solar system or look at certain exoplanet systems, they probably have these kind of oscillations at a much larger amplitude. And so in terms of climate variations on like 10 or 100,000 year timescales, they might be a lot bigger.
It's really fascinating. I mean, something that, as you're talking about the orbital dynamics and the settling of them and the interactions, I'm thinking back to what you were saying about was it the Orion Nebula, where the JWST saw all of these planets in binary systems?
Yeah, the Orion Nebula cluster. Yeah.
So it makes me think of, okay, so if you have a star that's just passing by a solar system, you have these really brief and ineffective interactions. But is it possible for a star to pass through a planetary and solar nursery like that and then come away with just a bunch of stuff that's kind of glommed onto it, and then as it passes, it goes through the great filtering process of losing things that are eccentric and stabilizing, and just kind of, I imagine like there's a really funny picture on the Wikipedia article for static electricity, which is a cat covered in packing peanuts. And so I'm imagining the sun like covered in packing peanuts of planets as it
the
leaves
cool thing
its
is
nursery.
those spinning pairs seem to already have that angular momentum that they would need in that sense. They're sort of ready to go if they were aligned properly. I mean, I'm just very wishful thinking here.
Well, it's not even wishful thinking. I'm just like thinking about how big and complex the universe is and how it keeps seeming to get a little bit longer. And so something that we talked to Gibor Basri from Berkeley a while ago about brown dwarfs.
Oh yeah, cool.
And it was really funny because at one point it was like, well, what's the difference between a brown dwarf and like a really big Jupiter? And the differences are really fine and nebulous because it's at some point you get to be big enough that you start to fuse, and when you've started to fuse, then you're classified as a brown dwarf. But before that, you're Jupiter. And ever since then, I've been thinking about the process of building stars in solar nurseries, and I'm like, okay, well, if the distinction between Jupiter and brown dwarf is simply a size distinction, and you can have something that just never accumulates enough mass and it remains a Jupiter, is it possible that you could get something that is smaller than a Jupiter in the same way inside of one of these stellar nurseries?
Like, are you saying, like, is it possible that some of these Jupiters are, like, failed stars also? Like they're like not even failed enough to be a brown dwarf. But
So it's like if you start from the ground, if you start from the super high entropy state where everything is scattered, and then you're slowly building things up that are bigger and bigger. You have one branch point, which is like, okay, we're going to go star. And you go star and you can get as big as you want along the star path. Then you have another branch point, which is where we can grow to brown dwarf, and that's where the limit is. And then another one is you grow to be as big as a Jupiter, and that's where the limit is. And it
is anybody considering the de novo formation of these Jupiter-sized planets? Do you know? I think that's what we're circling around. Is like, can you
it seems like
can you form a Jupiter without a star, or something like that?
Sure.
So this is a really good question. So, when it was last year that there was the first big discovery of like a large population of free-floating planets. It was in a different young stellar nursery than Orion. It's called Upper Scorpius, and we found about 100 candidates, and it's about 100. The reason it's about is because is actually related to what you were just saying, because there's a bunch of objects where we don't have good measurements of their masses. So we don't know their masses directly. We know them from how bright things are. If we know how bright these objects are and how old they are, assuming they're the same age as this cluster, then you can end up via a model end up with an approximate mass. But there's plenty of uncertainty, especially in the age. And so there's some objects, if the cluster is old, would be older than we think would be brown dwarfs. But if it's younger, then they'd be planets, right? With this kind of very rough division between the two. Anyhow, I'm mentioning that because among these 100 free-floating objects, where'd they come from? It was the biggest sample that existed at that point for, that we could analyze all in one shot. And so I was coming at it from the point of view of thinking that they were mostly planets that had formed around stars and been kicked out. But the people that I was working with were coming from the point of view, they thought much more about stars. And they thought that, these are probably just puny, tiny little stars that are so faint that we don't usually see them. And so in the end, we tried to estimate the relative contributions of both using some kind of relatively simple models and ideas. And we came out with the idea that we can't really nail down how much is, contributed from either one. But they're probably both contributing at some level. And so just the idea being, the short answer is, yes, people do think that very small stars would end up being kind of free-floating Jupiters, and they probably can form. And there's a little bit of debate about exactly how small they can get, but there's a lot of people who think that they do form that way.
Okay, so then the follow-up question to that is, how rocky can you get? So Jupiter's not very rocky. Yeah, so it's like in those conditions, if you're like, okay, so they're very small stars which are like Jupiters, I'm like, can you have something that's even smaller that's rocky along the same level of formation?
It seems like Rockies are really hard to see, right? Like you would like seeing a free-floating Rocky is just like
I'm not even talking about like, have you seen it? I'm asking theoretically, because my understanding of planetary formation is that you have this massive cloud that's around the outside of the star, and in that the disk gradually clears paths as it agglomerates things onto it, and it gets bigger and bigger and bigger, and then you have a planet. I know that there's something that's like, is it the pebble boulder boundary problem?
Oh yeah, there's lots of those boundaries or catastrophes. They used to be called catastrophes, but not anymore.
So it's like
those kind of thing.
There's this fuzzy spot of like how something rocky gets to be big enough to be a planet, because like at some point you have things that are big enough that when they crash into each other they break up into smaller things than like sticking together.
Exactly, yeah. So there's this kind of this barrier at like the size of probably little pebbles, and so like centimeter sized things. And so kind of in terms of growing things, that the key step in growth is thought to be the accumulation of those things probably directly into much bigger ones. And exactly how that happens is thought to be, that's a whole different story. but basically we think that those kind of small things, maybe something between the size of grains of sand to maybe pebbles, so like millimeter to centimeter size things. Those things can accumulate, get really concentrated in certain parts of the disk of gas around the young star. And once they get sufficiently concentrated, there's this kind of hydrodynamical effect that can keep concentrating them more and more until gravity takes over, and the self-gravity of that little clump makes it into probably not one, probably a whole distribution of what we call planetesimals, things that you think of like asteroid-sized things, like things that are, mountain-sized objects. And those are kind of the smallest, real, true rocky things that we think of.
Oh, go ahead.
Let me just say one more thing about what you were asking about. In terms of free-floating rocky objects, it's worth noting that microlensing has found at least one, with a few other candidates that don't look as good, but at least one really well confirmed, I think it's 2 or 3 Earth masses, free-floating object. And so those are probably very abundant. And so those fit nicely in the picture of when Jupiter's, are tossing each other around, the survivors' orbit gets really stretched out. A lot of stuff gets ejected from the system. It's not just that other 1 or 2 Jupiters that get ejected. It's all the other stuff that was trying to grow, probably including lots of small rocky or icy planets.
And I imagine that these star formation areas would be ripe for that sort of ejection and that kind of chaos, because there's a lot of things happening, and it's an increased density of interactions. And so to bring it back to the original vision of the cat covered in styrofoam peanuts, I'm like, if you have a star that passes through an area of such density, could it just agglomerate a bunch of things that had been forming, and then as it leaves just chaotically sort it and just form a solar system from all the stuff that it picked up?
This is very interesting. So there's two related things that I'm aware of. So one of them is there's one idea for the origin of our sun's Oort cloud, that it came mostly from other stars. In that, and the way to think of it is basically early on, another part of the story, right, is that the sun was part of this cluster of stars, like you're talking about, and that cluster doesn't last forever, but it's during that cluster phase, as you're saying, where a lot of the action happens. And so, planets are starting to form; they're kicking each other around. Each star is probably chucking out some amount of rocky or icy stuff. Maybe there's big instabilities that are even chucking out planets, but that cluster of stars itself only lasts a few million years, maybe 10 million years. And then it goes away, and those stars go their separate ways within the galaxy. And during that kind of phase where things are happening, but you're getting farther and farther away from your neighbors at the same time, that there can be, depending on exactly how fast things move, you can end up grabbing onto a whole bunch of stuff from your neighbors. And it wouldn't be captured very close in where the planets are. It would be more kind of trapped in the outskirts, like in the Oort cloud, which extends to, 100,000 times the Earth's sun, this 100,000. But that's when this kind of action could happen. For things to get trapped closer in is not very easy, because you need to dissipate orbital energy again. But it was actually shown in a couple of really cool papers that, a star with its disk that's forming planets is kind of a nice bucket. I like to think of it as a bucket zooming around within the galaxy or within the cluster to capture random things that go by. And so it can't capture big things because the energy is too much. But there's enough friction with the gas to capture small things, to capture some of these planetesimals that are zooming around. So depending on the angle and how fast they're moving, stuff like that, a disk can end up capturing some planetesimals, and can basically, those can act as seeds for a future generation of planets.
Yeah, speaking of the seeds, I was curious because, well, let me ask you this. Are any of those free-floating planets Neptune-like, or are they all hydrogen, helium, Jupiter type things?
Oh, I mean, so no one really knows, because we don't have any really good pictures of them. There's no resolved images of them because they're too far away. And I think this will be coming with James Webb in the near future to kind of get a better idea, to try to get some kind of more spectral information about them. So far, the lowest mass ones are thought to be about Jupiter mass. And the reason for that is just because you need to have the object have enough internal heat to be bright enough that we can see it.
Mm.
And so Neptune's,
I mean, the reason I ask
there's
about
plenty around there,
Neptune's
they're
is
probably too
because
faint.
they've got that their cores look a lot like a rocky planet in some sense.
Hmm.
And so it would be interesting if there was the potential for this evolutionary step where something that looked like a Neptune could transition, could get too close to the star and lose its outer layers. And that in some sense would be a path to a rocky planet too, because at least you would have the ability to accumulate a lot of material and compress it under all of that liquid and gas in the first place, and you might be able to get around that meter boulder pebble boundary business.
I mean, there is one idea that Neptunes can lose their atmospheres entirely if they're close enough to their stars. So that's kind of similar to what you're saying. But they would have had to already kind of get over that barrier to form the building blocks before they got to that point.
Well, if they had a lot more material in the first place, I guess if they look a lot more like a Neptune with all this liquid and gas and stuff that's sort of compressing all the rocks together at the center in a way that would, I just feel like could maybe overcome that pebble boulder boundary.
Oh, I see what you mean. The way that we think those planets grow is kind of from the bottom up. And so we think that you need to actually form planetesimals to grow larger things, to have enough gravity to pile the gas on, to get to the Neptune point, a Neptune stage or Jupiter stage or whatever.
So you need a little seed in the first place.
Yeah, that's the current thinking. There is a different branch of ideas that you can form them kind of from a top down, which is not impossible, at least in certain conditions. But we think most of them probably form from the bottom up, where you have to go through that, forming the planetesimals first.
Have you
And
seen
so
these?
even though that's a barrier, it's not that bad, because for 20, 30 years, it kind of stumped people thinking about how planets formed. But it's been pretty much solved at this point. And there's still debates about exactly where, exactly when, but it's pretty much agreed upon that that barrier does get crossed pretty easily.
And in terms of coming up with a big metal seed, like a big chunk of iron or nickel or something like that, have you seen these images of these supernova with these like huge iron shells being ejected? It's very, very incredible, striking pictures. When
they have different layers that they're burning.
And then when they explode, cool. There's just these layers of radioactive iron, like almost, they look like little chunks of iron just flying off into God knows where. And I just wonder if those could get involved in the formation of something at some point, serve as little seeds.
That's a good question. I know there's like, I don't know the size scale of those globs, whether you could really end up with a gigantic concentration of something like iron or nickel. There's been a lot of discussion in the solar system. From meteorites, we know that there were a couple key isotopes in the early solar system that provided a ton of heat. So one of them was an isotope of aluminum called aluminum-26. That's the dominant one, but also one of iron called iron-60. And they are thought to have come from a nearby massive star, either from its winds kind of before it went supernova or from the supernova itself. And so it's thought that was kind of a key ingredient in the solar system. And just to give you a sense of scale, at least the numbers I've heard is that the amount of heat released by aluminum-26 during the first 2 or 3 million years of solar system history is more than all of the heat released by every other process in the whole rest of the history of the solar system. So it's a big source of heat. And so that, imagine,
is that a condensation reaction?
Sorry?
Is that a condensation reaction or something? What is that?
Oh, it's basically, it's produced in these massive stars, and then it's just radioactive decay once it's in the solar system. It's got a short half-life, about 700,000 years, so it only mattered very early on, but it really fried things early on. So, and iron-60 also produced heat, but not quite as much. I don't know the numbers on iron-60.
I pulled up some of these supernova pictures of like Tycho and Kepler, and it's really interesting because if you look at it as an object with mass, right? Because like I would always look at supernovas as being these kind of gassy, just diffuse places. But I mean, It does seem like there's areas of density of iron that's
Like little blobs, right? I'm not
yeah,
looking
like
at the same
it's like
picture, but-
Tycho has like a very blobby texture. Like it looks like there's like little like chunks, but it's also not like particularly condensed. And so it does seem like it's really gassy. And so if it's really gassy and it's not like molten iron, because I think that the temperatures are so high that it's not like you can have like solid or even molten iron. I think that everything is ionized
think they're
during a
only able to-
supernova and then like gradually cools and then recondenses.
Yeah, then it turns but then it'll condense because its stuff's really refractory. So as
So
as it expands, it's got to cool down and condense, I think.
So there's got to be just like metal chunks somewhere just floating around, right? Because I've
I
always
would think
wondered,
so.
I'm like, okay, how does Earth get a core that's so metallic?
So dense too. Like we're the most dense thing in the solar system. It's so bizarre. It's like you would think that the really dense stuff would end up inside of the sun.
Yeah. Why doesn't it?
So I mean, I know Earth has the highest density of any planet, but that's just because of its mass. I think its uncompressed density is less than that of Mercury, for example. So Mercury has a higher, as a fraction of its total mass, it has more iron and nickel in it. Earth has, I think, 32%, if I'm remembering right, 32% by mass is its core. And the density just comes from the gravity of the stuff on top, squishing it a little bit.
Hmm.
And so that seems like across all the planets, that fraction is pretty similar, except for Mercury. I mean, across the rocky planets. It's different for Mercury, and it's kind of debated whether that's because Mercury started off with less rock, so more iron, less rock, or whether it started off with the same mix and something got rid of some of the rock. And so the kind of big candidate for that is a really massive impact during, late in Mercury's formation that would have stripped off kind of the rocky mantle, but left behind the iron core.
Hmm.
And Mercury's got a relatively eccentric orbit too, right? Seems like there must have been some history.
Yeah, it does. It has the highest eccentricity of the planets. Yeah. Yeah.
So
So
like,
where that comes from is it's actually Mercury's orbit is dangerous. It's not probably not from impact. It's probably from Jupiter and Saturn's perturbations. At a distance, Jupiter and Saturn end up exciting Mercury a lot.
because there's some diversity in the eccentricity amongst our own planets and in the orbital plane and the rotational axis. And Venus is a really, really weird one. I don't know if you want to take a stab at Venus's mysterious history, but we're doing that actually in my course right now at the university. I teach this intro astronomy class, and Venus is such an interesting one because in some sense it's so similar to Earth, but it's also just so different, and it's just behaves so strangely. It's like the strange redheaded stepchild.
Yeah. I mean, my understanding for Venus is that what is it? It's trapped in this weird. Its rotation can be explained by tides, basically friction between the atmosphere and the planet when you take tides from the sun into account. But for that to ever have happened, it had already had to be spinning quite slowly. And so why it was ever spinning slowly is still pretty much an open question. I've heard some people throw out the idea that maybe Venus had a moon. So our moon, is always moving slowly away from the Earth. And at the same time, it's slowing down Earth's spin. If Venus had a moon before, it would have done the same thing, kind of slowed down Venus's spin in time. And that whole process might have happened faster because it's closer to the sun. So maybe that can contribute to slowing it down, and then this other effect with the sun ended up putting it in its current spin state, something like that.
But isn't it's rotating the wrong way with respect to everybody else? And isn't it slowly coming back into rotating the right way, or slowing down at least, or something like that?
Oh, is it? I don't know about that.
I thought so. Yeah, I don't know.
It's possible.
Maybe I'm wrong about that. It's very strange. It's like almost acting like a moon. It's not quite, but it's sort of. Well, Mercury is tidally locked, right?
It's not locked. It's in this 3-2 spin orbit resonance where what does it do? It spins 3 times for every 2 orbits.
That's right. Yeah, perfect fifth.
Yeah. Yeah.
How
Not quite the
much?
tidal lock where it's always showing the same face. Yeah.
Mm,
Oh, sorry. Got a
it was
question.
that was for Venus. You're saying isn't tidally locked?
Mercury.
Mercury's not tidally
Mercury.
locked.
Venus is also not quite, but it does turn very, very slowly.
I thought that like a single day on Venus is like 300 Earth days.
It's longer than its year, I think.
Yeah, yeah, it's really slow. I mean, I know it's spinning. The rate of spin is super duper slow. Yeah, so it ends up being longer than its year, like you're saying.
So the Venus is slowing down.
Hmm.
It slowed down by about 6.5 minutes over the course of
Yeah, because I thought the
from
prediction was that it
1990
was.
to 2006.
I thought they were saying it was going to eventually get in step with everybody else and start turning in the right direction.
That'll be a day. What changes if the age of the universe changes?
The
Like,
age
let's
of the
say,
universe.
yeah, like let's say.
We had a guy on the show who was.
I mean, there's been lots of people that for a long time have been proposing that the calculations of the Big Bang are inaccurate, and that was kind of didn't have many legs, and then the JWST came online, and then there's all these like really weird redshift things. Like I saw this article the other day that was like I think that somebody found something that they think is like a massive black hole at the edge of the universe that they're like, that's weird, that formed 500 million years after the universe formed. And so there's you see the data coming out, and if it holds, and if the redshifts are so high, and if we are seeing these massive objects that are, supposed to be formed at the same distance from the birth of the universe as we are separated from, say, the dinosaurs, it starts to beggar belief a little bit, where you're like, okay, well, we could probably push this. And so we had this guy, Rajendra Gupta. He's an adjunct he's a physics professor at University of Toronto, I think.
He is both an adjunct and a physics professor.
That's really funny. And he basically laid out, he was one of the first people to, after the JWST, lay out a possible model for how it could be that the solar system is older than it, and not the universe. He doubled the age of the universe. He was like, conservatively, like it could be twice as old. And in the back of my mind, I'm kind of like, well, if we just keep building telescopes and we keep finding that we can see farther and farther, and we keep finding things that are older and older and more anomalous, I can see it extending even more. And so when we talk about planetary formation, we have this like 4.5 billion years for the solar system. And I'm like, does it change at all if the age of the universe suddenly doubles or triples or quadruples? Can that suddenly become just a measure of, the last time that everything here melted because of some cataclysmic event, and then is just the reflection of something that's much older? Or is that just, do those two things not play with each other at all?
I don't know. I'm trying to imagine how it would affect the formation of the solar system directly. As long as the solar system itself is how old we think it is, I don't think it matters that much.
Well, we have,
I mean,
so one thing that I'm really curious about is I'm like, okay, how well do we know how old stuff is in the universe? I know that we've found, or in the solar system. I keep using them interchangeably. I have like a very 1920s perspective on on the extent of the universe. So it's like we have some rocks. We have dated the rocks. The rocks all point to 4.5 billion years. But what happens if we date stuff from, let's say we take like a core sample on Mars? Because most of the stuff that's on Earth from Mars is ejecta.
Yeah.
And so I can imagine that if 4.5 billion years ago, there was like a really fiery period where everything got like really melted. And so now you have stuff coming from Mars that is 4.5 billion years landing here. We date it. Okay, it's 4.5 billion years. But say you go to Mars and you drill and you find some granite on Mars, and it turns out that it's a lot older than 4.5 billion years. Is that possible?
That would be super interesting. I mean, I think everyone would be super surprised by that. But if it happened, it'd be really cool. I mean, I'm of the opinion that really unexpected discoveries are the best. So it'd be really interesting. So if that happened, then we'd see what was up. I mean, there's a lot of pre-stellar grains that are found these days. In meteorites, I believe, and also I think they're also found just kind of floating around. But I don't know a ton about them. I think they're within meteorites, and so those are grains that are dated to be, up to a couple billion years older than the solar system that got incorporated in rocks as the planets formed.
Oh, that's very
And those little bitty parts of the rocks were older than most of the rest of it. And
Mm.
so if it turns out that Mars was formed from stuff that was older than Earth, what would that mean? I don't know. I would be super confused if that happens.
Because I mean, like with the moon too, the parts that we've dated, it's like surface regolith. If there, because I always wonder, like, if it's possible to find something that is older than 4.5 billion years, and
They actually
are
had the complete opposite problem. I saw a headline this week, maybe you saw it too, about these Mars meteorites that were way too young that they recently found.
oh
Did
really?
anybody see this?
Mm-mm.
Oh no, I didn't see this.
It was like 200 million year olds. They dated these Mars rocks to 200 million years, and they were trying to come up with explanations for basically how their dating system had failed and how it had incorporated some sort of new argon or something like that into it. Yeah, I have it open on my computer. I was going to email that. I was going to see if these people wanted to talk.
Most meteorites from Mars are just a few 100 million years old.
There you go. And so the explanation was not that they actually are a couple 100 million year old, but that there was just some incorporation of fresh radioactive isotope coming anomalously during their transit, which is like really interesting because, yeah, the dating techniques are wonderful because you can cross-check different isotopes in one sample, which is really cool, and make these isochrons. But at the same time, if the thing melted and incorporated new stuff, it's very difficult to tell that from its birth in the first place.
It's interesting because
that's really tricky.
I'm looking at the article right now, and it seems to suggest that they think that it was from like volcanism.
That's when it incorporates fresh stuff?
Mm-hmm.
Interesting.
Yeah, that's really interesting. I know, like, there's that issue of, like you're saying, resetting the clocks. Basically, when something happens, can reset the isotopic clock. And so then what age are you really measuring?
Yeah. I mean, in terms of what Nazi was saying about like the age of the universe, I think that it only starts to matter at the upper limit, because if the universe is only twice as old as we think it is, like 30 billion years or something, it's like not much changes. But if the universe is trillions of years old, then you have the opportunity for lots of crusty leftovers from stars to be contributing to solar system formation, which is because a pretty common pathway is just not that stars supernova, but that they just kind of peter out. And but that takes trillions of years, from what I understand. So it's like it's not really even part of the calculation at this point.
I mean, so I hold out some. I know that we have the cosmic microwave backgrounds. I know that we have like massive red light shifts from the edge of the universe, and so the Big Bang has a bunch of evidence for it. But I'm like, it still is a theoretical construct that has a lot of data that points to it, but we have believed crazier things for longer about how stuff works. Like, we believed in spontaneous generation for, like 2,000 years in biology, where it's like stuff just comes from nowhere.
Well, we thought the whole universe was the Milky Way until like the 1920s. So.
And so, like, in the back of my mind, I'm always like, okay, so maybe this stuff is true, and maybe this is accurate, and maybe this is the theory that 10,000 years from now, everyone will agree that this is, the Big Bang happened and this is how it works. But sometimes I try to take the longer view, and I'm like, okay, 10,000 years from now, will we still believe this? And if we don't, if we realize that the data is actually pointing at something different, and it's not quite the Big Bang, and it's not the origin point of the universe, and like, if we set that aside and like explore down that path, is there actually an upper limit to the age of a universe? Because I know for a long time that there was the belief in like the steady state universe that Hoyle was a big proponent of. And Hoyle eventually came over to the Big Bang, I think after he saw the CMB and after he couldn't come up with an alternative explanation for redshift. And so like even Hoyle at some point saw it, but I'm like, okay, so let's say that there's some doubt is cast upon the current theories. Is there an upper limit to the age of the universe? And if there isn't, doesn't that mean that all of these unlikely events somehow become likelier?
So
The likelihood, yeah,
this is a
likelihood.
tricky one. So I don't know if there's an upper limit on the age of the universe. I know there's a really cool book, I think it is, or paper by Fred Adams and Greg Laughlin about the long-term future of the universe. And they look at all the stages of what would happen in the future. And so if the universe was older, you'd just be kind of further along that. Assuming that all the numbers from physics that we still have those same numbers, but the universe is older, then more stuff must have happened. And so more stars must have already been born and died. There's got to be a lot more leftover junk, a bunch of more leftover white dwarfs, more leftover pollution from supernovas, more likely for stars to be burning out and stuff like that. If it's way, way, way older, then that would matter. If it's a factor, if it's twice as old, it probably wouldn't make a ton of difference. And so I don't know. I don't know it, about those a ton about the very, very long-term things like protons decaying and things like that. But I know that people have started to think about it, what it would look like on trillion-year timescales or whatnot. In terms of probabilities, it's sort of true. Like if a certain event has a certain amount of chance to happen, you wait longer than it can happen. It's the whole monkeys on a typewriter thing, right? That's the exact same problem. You wait long enough, then monkeys will type out whatever you want, Shakespeare or whatever you like. And so, like the star flying within 100 AU of the sun, it's got a 1% chance of happening in the next billion years. But if we were able to just kind of stretch out the clock forever, then it's totally going to happen at some point if you wait long enough. Ignore the sun's going to become a red giant and all that. So at some point it'll totally happen.
Yeah, Nietzsche takes this idea to the limit with his eternal recurrence idea. Have you encountered that?
No, I don't know this.
Yeah, so Nietzsche was a big proponent that there was no age for the universe, and so he basically figured that since eternity has no bounds on it, that everything would happen again. Essentially, you would run out of options of things to happen, and so you're basically doomed to keep living your life over and over again after gazillions and gazillions of years, which is
like
an interesting
Groundhog Day, the movie. For
basically, yeah. It kind of makes sense though. It's like, it's hard to imagine no bounds on time, but if you had no bounds on time, I guess another planet like Earth will eventually happen, and it'll eventually have some people on it, and eventually maybe one sort of like you. And
yeah, totally.
Speaking of planets like Earth, I know that one of your projects is basically to imagine these other alternative worlds. What goes into that?
Oh yeah, so that's a whole other can of worms. So that happened because I started writing a blog, which I started writing because I always thought it'd be fun to write a book. And a friend of mine, Caleb Scharf, who writes really good books, he said, "Well, you should start small, start writing a blog and just kind of practice." And so I was like, "Okay." I started a blog, and I was like, "Well, what am I going to write a blog about?" And I thought, I don't know where this idea came from. I probably stole it from somewhere. I can't claim it to be original or anything. So my first idea was like, what if, the solar system was just better? Like, how can we make the solar system better? And so I played a little game saying, okay, I can keep all the planets and moons in the solar system and all the orbits, but I can move planets and moons onto different orbits. What would I do? And I played around with it, and I ended up with a system where, let's see, what did I do? I put Jupiter, I think, on Mars's orbit with like Venus around it and stuff. Anyway, I moved things around such that I argued that I had created 7 habitable worlds in the solar system instead of just one. That was kind of fun. And then I kept blogging and I kept writing about other random stuff. And I would look at my stats, and this post about making a better solar system was the only post that anyone ever looked at. And so I thought, okay, I guess I'll, if this is what people are interested in, let's explore this more. And so then I kind of got rid of those other restraints and said, well, if I was going to really build a planetary system from scratch, how would I do it? And so I kind of laid out, choosing what star would I choose, kind of planets would I choose, and kind of the key thing that built on the experience that I have from doing planet formation stuff is what orbits would I put these things on. And so I went through the whole process of building the ultimate the ultimate solar system, I called it, and ended up with this system where there were different rings of planets, and each ring had a few different planets on it. For example, you could have in one system there was a Jupiter on each orbit, and Jupiter could have moons that were kind of Earth-sized moons. And just like Jupiter has these kind of packs of asteroids that are trapped in Lagrange points in front and behind of its orbits, at what are called the L4 and L5 points.
The Trojans.
Those could actually house planets. Oh, sorry.
The Trojans.
Yeah, exactly. The Trojans and the Greeks. Now we just call them all the Trojans. But yeah, so these Trojans, basically, so you can have Trojan planets there. So I put Trojan planets there and ended up with a system with like 30 habitable planets in a given system. And then I got a lot of response. It was kind of fun to do, right? And so I kept building on with more and more ideas of how you could do this. And I ended up with systems that have hundreds of planets in the habitable zone. And I didn't want to just tell people to believe me. So I ran n-body simulations to show that they are indeed stable when I would produce these things, just to kind of demonstrate it. And they did get kind of bigger and bigger and crazier. But in all of these were kind of created such that they're dynamically stable. So if a system existed, then it should be able to evolve and maintain that same orbital configuration and stay stable. But in many cases, it got to the point where it was complex enough that it was hard to imagine how it would ever get into that state in the first place.
Mm.
But if it could ever get there, then it'd be stable. For example, one thing that's kind of interesting that people have shown before, and I kind of adapted, was that for us on Earth, we have one planet that orbits around the sun on almost a circle. But it turns out that if you took 42 planets that were Earth, exactly like Earth, spread them out evenly on Earth's orbit, you can even leave all the other planets in place. It's perfectly stable. So Earth could have 41 brothers and sisters along its same orbit and remain totally stable. How would you ever get that in the first place? I don't know, right? Maybe you could have
are the
kind of ring
intervening
of gas and dust that would collapse like that. I don't know.
Are the intervening numbers also stable? Like if you have 2 Earths, 3 Earths, 4 Earths, and progressively more, do you have to immediately have 42?
You have to jump to, I think it's 7.
Ooh, that's not a
There's
good number.
Yeah, I know. It's weird. I tested, there's some theory behind this, and I tested it out, and you have to jump a little bit at one point. But basically, above some number that's stable up to 42. 42 is the maximum. And beyond that, beyond 42, each kind of pair of planets along the orbit is a little too close. So in the time scale of like 100 million years, it'll go unstable.
It seems like it could be really, in some sense, predictive and technologically useful in terms of sorting out potential life-bearing solar systems that we might. Because I have this thought in the back of my head that all space exploration is essentially aimed at finding us a new home eventually. It just seems like everything is. I mean, I know it's a really ridiculously long-term project. I imagine this is thousands and thousands of years, but when those people eventually look back, they'll kind of see what we were doing now as the early stages of them making it to these new worlds. Because like you said, eventually, I mean, if we don't get hit by an asteroid or something, the sun's going to eat us. And so it seems like it's a noble project. And I wonder if these kind of simulations can give you some insight into what a really ideal solar system might look like, that we could, like, are there traces and signatures that you could pull out of these simulations to kind of, aim us at something?
Hmm.
Yeah, that's a good point. So that's kind of where we've gone in the last couple of years. Is I've ended up writing a couple papers on this kind of idea of planetary systems that we don't think could form naturally, but they're totally stable. And we even did simulations where we tested their stability for, billions and billions of years with the sun evolving. A star like the sun evolving, becoming a red giant, then becoming a white dwarf, and the orbits of these things expand, but they stay stable. And just to see, and so then in the end, if we ever found something like this, and we tested a few different cases, right? There's one case was the one I was talking to you about with rings of planets, but there's also, we tested another idea that I think David Kipping was the one who had it. So he came to me with this idea of saying, could you have a chain, basically a planetary system where the orbital period ratios of each pair formed consecutive prime numbers? And so would that form naturally? We've run zillions of simulations to try to reproduce the actual planets that we see around other stars. And we somehow never end up with this kind of configuration quantitatively, right? Qualitatively we do, but not quantitatively. And so it seems like a pretty good signature of something. And a system like that would survive for bazillions of years. And so we were arguing that if you ever found that, it's a really good candidate for, a very advanced other civilization. It's at least a good target to go look at and see what's going on here. Either there's some bit of physics that we missed completely, or something has created a system and put it in a configuration that we don't think could happen naturally. And so it's so kind of fun to think about, and it's fun to imagine, where are these kind of humps that the only way over it is to use technology or something else to get there, so that if you ever see something on the other side of that hump, there's something interesting going on. It's worth looking at. And so that's kind of the astronomy point of view of all these blog posts that I've done, is trying to see what it would mean if you ever really found these things.
And I don't know that we'd want to go visit somebody who's been around for that long. They might not be happy to see us.
Old cultures tend to be very friendly. You show up, there's a lot of hospitality.
Sometimes.
For your tea, yeah. Hey, how about we take a little break? I want to get up some more coffee.
Sounds good.
Okay, let's do it. We'll be back in just a few minutes.
Okay, sounds good. I'll be back in 5 minutes.
Thanks.
Of course. We are delighted to announce that Demysticon 2024, our very first scientific conference, is officially launched, and you can buy tickets right now at the link in the description, and also in the link that is up in either this corner or this corner. We are going to gather in Austin, Texas on April 7th and 8th of 2024 for 2 days of talks on consciousness, mythology, archaeology, solar physics, hypnosis, and much, much more. Buy tickets now, up at this link. We were talking during the break where whenever we get astronomy or any kind of space people, I feel like we always are frightening to them a little bit, because we're like, well, what if the Big Bang didn't happen? What if the Earth comes from another solar system? And people are always like, no, that's not possible. And we
wanted to apologize for being so batshit crazy, but we're interested in the far-flung impossible possibilities, near impossibilities.
It's okay. No, I don't mind at all. I think it's great fun to think about this stuff. I mean, as you can see, like, there's a lot of things for which I have no answer at all, but it's still fun to think about. One thing I was thinking about that I didn't quite get a chance to say is when a supernova goes off and shoots out a blob of metal. I mean, combining that with your previous idea, imagine capturing that in orbit around a star or something, and you go exploring. You're on one planet, you go exploring this, what you think is another planet, and it's a giant blob of metal. Could you actually tell that it came from somewhere else or something?
Or would it just look like Mercury?
I don't know. Yeah, maybe. Who knows?
Well, isn't NASA just launched a mission to Psyche, which is...
Oh, yeah.
Do you know about this?
Yeah. I know the mission's called Psyche itself, yeah.
So
yeah, I know the PI, Lindy Alkenstanton, yeah.
I've been trying to get her to come on the podcast, but I think that she seems busy. But
what's the deal?
For sure.
I just think with Psyche,
Yeah.
So it's like it's this really metallic object. They think that it's the core of maybe an early planet, but in terms of it just being a loose metal object in the solar system. It's in our solar system. It's between Mars and Jupiter, and it's just this like weird metal thing that's floating around.
Interesting. How big is it?
It's a great question.
That's a good question for someone who has Google up right now.
Yeah, right. How
We'll
big
get
is
to the bottom of this.
Psyche? I will get to the bottom of this.
But you should totally try to have Lindy Elkin Stanton on your podcast.
How do
She's
you-
fantastic.
Wait, what? How do you spell?
I've emailed.
Oh, you've
She's in her
already-
inbox. We're we hit the handler. There's some lady at NASA whose name is Gretchen, and we've been shunted to the handler. And so I'm trying to convince the handler that, because I think that she's like, well, we can have somebody come by for like 20 minutes and like do like a little question and answer session. And I'm like, well, we do 3-hour podcasts, and she's like, I don't know about that. So
yeah, there's always
but
several
it's-
layers of NASA people to get through. Every NASA person we've had has been a really interesting. They're all very different, but very complicated interactions.
So this thing is crazy. This thing is 140 miles in diameter. And it's just, I don't know, is that a normal size for an asteroid?
It's one of the bigger ones, but yeah. The biggest one is Ceres, which in diameter is almost 1,000 kilometers. So what's that, 600 miles?
Wow.
Yeah,
So my only familiarity with Ceres comes from watching The Expanse.
Oh, I've read the first book and a half, but I haven't seen the show. Is it good?
We got really hooked on it for a while.
Yeah,
It gets a little crazy at the end, but
I don't think that we finish. There's a lot of shows that we never finish.
Yeah.
And I think The Expanse, because it's like there was like months between, because at some point Amazon bought it and Amazon was finishing it and like it wasn't on Sci-Fi anymore. But the first 2 seasons are just really, really, really good. And
Oh,
like
yeah.
very,
I get it.
because
It
you've
goes
read
like-
the books, so you know that it's the contact.
I know where it's going, at least at the start. Yeah, I really liked it. I would like to watch that. That's in the category of shows that my wife doesn't want to watch with me,
Aw.
and so
Oh, because you're gonna be you're gonna be talking about how like nothing makes sense.
partly that, or I don't do too much of that, but she doesn't love too many of the sci-fi shows, and so I
Mm.
watch them with my older son sometimes. But we have a backlog of things to watch that we watch together, like Foundation or something, and so I haven't had a chance to see these things. So I'll have to check it out.
I really like the exploration of the themes around different populations of humans inhabiting different bodies in the solar system and like how the politics of that would play out. Because, people talk about going to Mars right now, and, Elon Musk is all, I'm going to go to Mars too. And I'm like, I feel like it's going to just be a freaking slave colony. Like, who's going to want to live underground in these caves? And I don't know. You could just see this really dystopian version of this where the wealthy, nice, well-to-do people keep the Earth for themselves and sort of just send off the huddled masses to these godforsaken rocks. I don't know. I like that exploration. in the
There's
show.
a
Yeah, I found that
really,
really interesting too. Yeah, can imagine lots of creepy things like that.
there's a really. Do you ever read any Philip K. Dick?
I've read a couple of books of his. I read a book of short stories 6 months ago or something.
His short stories are really, really, really creepy. But he has this book called The 3 Stigmata of Palmer Eldritch, and he places it on a different planet where there's all these colonists, and the colonists are supporting themselves.
I think
through
it's
the-
Mars. It doesn't matter.
Yeah, I don't know. Maybe it's Mars. Doesn't matter. The point is that the colonists that live underground support themselves on the consumption of massive quantities of this hallucinogen called candy. And
Because they're so freaking depressed, basically.
so the only thing that keeps the entire situation going is that they have this hallucinogen, and then the hallucinogen gets interrupted, and so like the entire the arc of the story unfolds on the basis of that. But it does seem like in order to move to a new planet that's completely barren, dead of anything, it just the human spirit seems to need something of nature to be able to flourish. And in the absence of that, I feel like you'd have to rotate people out after just a couple of months.
I imagine. I read these books just recently. I forget what the first title is. I forget the name of the author even. They're called the Lady Astronaut series, and it
Sounds very dainty.
envisions basically it envisions a different path, for history. If there had been this asteroid that bashed into Washington D.C., it turned out in the early 50s, I think it is,
Hmm.
and then it imagines this kind of other future. where there's a lot more colonizing space because they're worried about the Earth maybe becoming uninhabitable if the greenhouse effect gets too strong. And so there's a really big push for this, basically for space exploration. And one thing they have is there's the third book that I just finished is set on the moon, on the space base on the moon. And I'm not giving anything away in case you want to read it. But there's a kind of a small patch where they grow, weeds, basically like dandelions and stuff. And apparently it's the place that everyone loves the most. They all go and want to hang out there to be around something that's growing, to be around nature as much as possible. So kind of going
It's really interesting because I feel like people weren't really concerned with asteroid impacts until they saw that Shoemaker-Levy thing back in the 90s. Because you see this, that program, there's a program, I forget, it's called like Space Guard or something, where they started tracking these near-Earth asteroids. Yeah. And there was like this congressional hearing. I read it to my class the other day. It was kind of crazy because there was like a NASA official on the podium and the congressperson was like, are we prepared to, if we do detect one of these bodies, are we prepared to, and they were like, that would take like 5 years to get a spacecraft in orbit to do anything about this. And so Congress was kind of like, all right, figure it out. And they kind of did. They managed, I guess, at this point to have tracked more than 90% of those objects that are more than, I think, a kilometer in diameter. And they also have started doing these asteroid deflection experiments too.
Over 140 meters, it looks like.
Okay. Okay.
Oh, yeah, initially the Space Guard goal was initially it was just down to 1 kilometer because those are the ones that they thought would cause global catastrophe.
Right.
But then once they got 90% of those, then they went lower.
Mm.
When I was in grad school, I did a project to try to repurpose this telescope to see, basically to try to find a bunch of them. And I was kind of making a pitch to repurpose this telescope by doing kind of simulated detections of what you might find. And I did not convince them to change it, unfortunately.
Interesting. They were just kind of like, no, we found enough? Or what was the...
I think it's because the telescope was designed more for studying galaxies and stars and stuff. And so this would have been kind of a big shift in their focus. And it was not what people wanted to do, which is fine.
I mean, it's kind of incredible that they managed to do that much in 30 years to reorient our entire human project towards being aware of what might come from above it. Because I feel like the Chicxulub hypothesis wasn't really accepted until like 10 years ago, which is pretty wild. I guess they found these little traces of the molten rock. I forget what they're called. Are they like techites or something like that?
Oh, like the tektites?
Tektites, that's it.
I remember that, yeah.
Oh, yeah. So apparently like it was only endorsed in March of 2010.
That's right, yeah.
Which is crazy because I feel like I've always known that the asteroids have killed the dinosaurs. But maybe I'm just like retcon.
The Alvarez paper came out in 1980 something. And so it waited for 30 years before being more widely accepted. I had thought also that it was just basically accepted like plate tectonics or something, where there's still a few random people who don't buy into it for some reason, but it's generally accepted that that's what's going on.
We've actually talked to a couple of those people on the show because one of the missions of the show is to be able to to talk in all quarters. And there's this guy Marvin Herndon who has a decompressing Earth theory, which is not so back in the day before Wegener proposed plate tectonics, there was this other guy, Sam Warren Carey. And Sam Warren Carey did a bunch of work to show that you actually can fit the continents together really well on an Earth that's like 70% of the present size. And everybody was like very perplexed and...
Well, he didn't have a mechanism for it, was what it came down to.
Yeah, and so a lot of people that are still big proponents of expansion are like, there's new matter being made at the heart of the Earth, and it's the creation of protons that are causing the expansion.
So Earth would actually be expanding, and it looks like everything's getting apart because Earth itself is expanding.
And so they point to
if you look into the history, it was like pretty seriously entertained in opposition to the plate tectonics idea.
It was like exclusively entertained.
Yeah,
and
for a minute.
Yeah, and so I think that
because you got to remember the plate tectonics guy. Wegener, he didn't have a mechanism either because they didn't have those convection conveyor belt things in the first place, and he was kind of laughed out of the room for a while.
And he was also not a geologist, he was a meteorologist. And so he put his entire life on the line to propose plate tectonics. And so they had to choose between two mechanismless theories. And tectonics, I think, had more of a mechanism because
It came around later, yeah.
I think that Wegener was the one that proposed the conveyor belts. Yeah, because he needed to have some way that the continents could float around. But Carey was never able to propose a mechanism. And so there's still some people
So this guy Herndon came along, I guess, is just to wrap it back to that. Because Herndon was like, hey, what if the Earth, like we were talking about earlier, was actually started at the core of some huge Neptune-like thing? And that compressive dynamic squished it down, basically. And when it lost its atmosphere over the eons, it just elastically decompressed, essentially, and left these continent ruptures, essentially, which is pretty far out there, but
and he's this emeritus geochemist, and just
he's been on like the cover of Discover magazine and stuff.
He's written dozens of published papers on this, and has spent his career trying to work out how this is possible. And he makes a compelling presentation, but it's like one of those cases where I feel like
not popular.
It's not only not, I mean, it's not popular, but it's also, does it matter? Does it really change things? Like, is it, how important is it if it is expansion versus tectonics? Because expansion, if it did happen, probably happened a super long time ago. And now we do have tectonics, and so it's one of those cases where it's like, if then...
Well, he makes the case that the ocean floor is only 200 million years old, so that last event may not have been that long ago in his conception. Anyways, it's pretty far out.
But
that's interesting. That's a common theme. Like, you see people, especially as they age, holding on to certain ideas more and more strongly. And I mean, I don't know. I always learned this stuff as plate tectonics being basically a fact. And now, since I do models and stuff, I realize that it's not a fact. It's like, a theory. It checks all the boxes pretty well.
I mean, Venus plays into that.
Sorry?
Venus plays into that factuality thing too, because Venus is strange because it should have all that convection too. Like, it seems to have a lot of the, what's for better, I don't know. It
has a lot of volcanism, but it doesn't have the same sort of plate tectonics, and no one really knows why that's the case.
Yeah, it's in this stagnant lid mode. Yeah, I've been to a bunch of meetings where people model this and they have cool animations of this, and they seem like they can explain it relatively well. I forget what the exact key thing is. I mean, there's something about water content reducing the viscosity, making it easier to have convection in the mantle. There's some other thing about I think ink exchanges with the surface can end up basically building up the crust to get so thick that at some point it can't do the whole subducting thing.
It also doesn't have a moon, too. I read an interesting theory. Somebody was looking at the internal heat of the Earth, and they realized that the balance, it should have cooled more than it has, essentially, over the course of its life. And they ascribed that to the moon being basically tidally churning the innards and causing friction interiorly. And it seems like if Venus maybe didn't have a moon, I don't know how that would play into things, but I don't know. Maybe have you ever tried to model Venus with a moon?
I've never modeled Venus with a moon, no. But like I was mentioning before, I mean, that's one idea for slowing down its rotation that's been thrown out there. And in principle, there's no reason that any of these rocky planets couldn't have a moon. We think that they all grew from giant impacts between big things. And towards the end, certain giant impacts will form moons. Basically, which ones? It's the ones where they're kind of a little bit off center. So, you spin out some stuff. Everything doesn't just glom into one big object. But they're slow enough that they don't just kind of bounce off each other. So you kind of get this thing where you spin out a bunch of material that ends up forming a disk. And then out of that disk comes a big moon. But that doesn't happen every time. And so once in a while it happens. If it happens and then there's another big impact, does that survive, or does the pre-existing moon get lost and bash into something else, or does it bash into the planet? These kind of things are probably all happening, and if one out of every 4 or 5 big impacts creates a moon, then kind of flip a coin a few times and you end up with one big moon in the inner solar system. That's it.
Yeah. With the convection stuff, it was really interesting because after we talked to Herndon, and one of the guys that's in our Discord is really into expanding Earth, and we kind of took it upon ourselves to look into the theory as, this is what people used to think, and this is what we think now, and this is all the evidence for the theory that is the popular one now. And I remember having this really disturbing moment when I was looking for evidence of the convection conveyor belt mechanism. Because you have this ridge on the bottom of the ocean, and the ridge is supposed to be a spreading ridge. And so technically, you're supposed to have this rising column of magma that lives underneath it that pushes the ocean floors apart and then subducts down underneath the continents. And that does not appear to be the case. And I remember being really disturbed looking at the magmatic maps because I'm like, that doesn't make any sense, and it's not where it's supposed to be. And there's this like giant blob of something that's like coming up under Africa. There's like a couple of different places where it's coming up under North America and like Australia. And there's this atlas of
You're talking about the mantle plume things?
Yeah, the mantle plumes. And there's this atlas of mantle plumes that you can go explore. And so I just spent days like trying to map where the cells were supposed to be. And I was like, they're not where they're supposed to be. And I don't know what to do with this knowledge.
That's too funny. That's fine. I have a lot of things like that where I know a decent amount about certain things like orbits and stuff like that. There's a whole bunch of things that I can spout off about a little bit. But if anyone asks me like really detailed questions, be like, "Oh, why is it like that?" Then I'm lost, and I'm like, "Oh, I don't know." It's funny. Like, I think we all have this big swaths of our understanding where we have vague pictures, but we don't have all the little details in there, and it's really hard to discuss those in detail without wanting to kind of fill in the blanks with just whatever we think should work on a whim, And so it's very hard to kind of hold back and be like, I actually don't know the answer to that, rather than say, I bet it's this thing, and just kind of make up something in the moment. I don't know if you ever find yourself doing that.
I like to speculate a lot.
There's really like two huge traditions in science there's a huge war going on. If you look back over the history of the last few hundred years, which is the like extreme empiricists and the rationalists. And the rationalists are totally fine with hypotheses. Like if we can imagine a way for this to happen, then we should talk about it. And the empiricists are like, whoa. If you don't see it, if you haven't seen it happen, we're not talking about it. And I think we live in an empirically dominated science world today. But it's interesting to look at the tango of the two across the ages.
Oh, totally. Yeah, I guess that my whole field is by necessity rationalists, because we're talking about stuff that happened billions of years ago or super far away that we can't test directly, at least not as easily as we'd like. We're trying to find, indirect tests of it, but we can't like just play back the movie of how the solar system formed and be like, yeah, see, like I told you, this thing happened. Right? It's so indirect that you got to be willing to entertain kind of crazy ideas. And it's really the kind of game between like coming up with the craziest idea you want. You can make up anything you want, but then you gotta test it. At least in a computer, even if we can't go back in time, gotta at least make sure it follows gravity or hydrodynamics or something like that, and it makes sense internally. And there's a lot of these. There's tons of papers out there, and I've written plenty myself, where you kind of figure, the story of the solar system is like a book, and you can't hope to write the whole book in one idea. So you just kind of pick one chapter and say, I think this process is going to explain a whole bunch of stuff, that stuff. And then you do some study where you're trying to show that if this, then that. And, sometimes it works. And when that's the case, it's kind of cool. But a lot of the times people show, if A, then B, but they never show why A would ever happen or how A would ever happen. How would we ever get to those conditions where this process that you just came up with would solve all these problems? And oftentimes it never could happen, right? So it's a leftover chapter of some book that never got written. But it's a very tricky thing to do that, because you want to come up with as crazy things as possible, because we don't know that what chapters are missing, and it's worth considering anything, no matter how crazy.
And in some sense, the earliest chapters are the hardest to read, right? The ones that involve the furthest away in time. It's like it's really hard to know the further you look back.
Which is why I think we rely so much on physical laws, right? Because you start with the realm of
What's possible?
quantitative assessment. And this is actually one of my favorite things. I've been reading a lot about Newton and Descartes. And Descartes was one of the only people in the last 200 years who was really aggressively
500
searching.
years.
Huh?
It was a long time ago.
I guess he was
1600s or
like
something?
400 years ago. Dang. He was like the only person in the last 500 years who was really aggressively searching for a mechanism for gravity. Where he was like, no. The only thing in the universe is motion, and motion is bodies impinging on each other. And so if the planets are moving, they're moving because something is touching them and something is causing them to move. And so he had this idea of the plenum, where like the solar system was filled with stuff. And there were these rings of like moving plenum that were moving the planets. And he was trying to like make a deal with the church because it was still important that the Earth didn't move. And he was like, no, the Earth isn't moving. It's the ring of stuff that it's in that's moving. And so he was trying to like retcon his mechanistic universe with the teachings of the church. And then Newton came around and was like, you can't have the plenum. You can't have anything that fills the space between the planets because they will slow down too much. And he had math that he could use for dynamic stuff and explain why Descartes was wrong, and went so far as to say that, you know what? Not our job to explain what gravity is. I can give you the equation. The job of the experimental philosopher is to come up with the equations that describe the motions, but we don't have to come up with what this is. And literally nobody really ever afterwards preoccupied themselves with the question of like, well, what is gravity? Because we have really good equations for it. And there's, Descartes is still just like rolling like a turbine in his grave because no one's been able to answer it. And it seems like the mathematics people are happy with the math because the math gives you the ability to say, is this possible or is it not? And so you can go all the way back to the beginning of the solar system or whatever, and the math still has to hold. And so you can hang out there, but like there's this other part of it that's missing where it's, okay, well, what does the math mean?
That's really a good point. Yeah. I mean, everything I'm talking about is already starting from that math part. So just assuming gravity works and going from there, not why does it work? What's really going on? Yeah. It reminds me of dark matter, the old dark matter thing of, this mysterious thing that explains so much, but it's weird because we can't touch it. Where the heck is it? What does it actually look like? And no one knows what it's actually made of, but everyone pretty much agrees that it's there. It's very confusing.
I don't know much about why it can't be ordinary matter. Do you have like a nutshell explanation for why
like cold invisible matter?
Yeah, because I'm always like, okay, so if there's a bunch of stuff that's being formed in the galaxy, and is just kind of frothing out to the edges, why can't the edges of the galaxies just be filled with cold stuff that adds mass but that we can't see? Like, what is the mechanism by which it has to be this like dark, mysterious matter that
It'll
doesn't
just take too long?
I don't actually have a great answer. I know this has been figured out because it's been explained to me before.
Okay.
But I don't know exactly why off the top of my head. I can remember a few things, right? It can't be certain things that you could see. So it can't be anything you can see because people have been looking for it and haven't found it. It can't be a bunch of dust because dust would be detectable at certain wavelengths of light. It can't be one thing that was proposed back in the day was maybe it's just a whole bunch of Jupiters, right? Like free floating Jupiter mass things, right? It's not stars because we would see them, right? But maybe it's these things like Jupiters, because those are pretty massive. If you have enough of them, they could be dark matter. But they actually tested this with early microlensing experiments. The Macho experiment tested this and didn't see, I don't know if it saw any, but didn't see enough anyway of Jupiters to explain it. So it's not that. It's none of this kind of ordinary stuff. Right? Is there any size range where you could actually hide a bunch of mass? Maybe. I'm not sure. I know people have thought quite carefully about this. And I remember hearing an explanation as to why it probably was not baryonic mass at all, but I don't have it off the top of my head, I'm afraid.
That's totally fine, but that's something that I've wondered about for a long time, so I will continue to pursue that.
Hmm.
So what are you working on right now? What's on the front of your desk? Or what are you what are your plans for the immediate future?
I'm doing one little side project. So the project that I kind of just wrapping up now is the one about, shooting stars by the solar system that I was mentioning earlier. And one offshoot of that is one about the moon. And it's kind of a philosophical one where people have long considered the moon to be kind of this really beneficial thing for life on Earth. And so the main argument that's been used is that the moon, at least currently, it stabilizes the Earth's spin axis. And without the moon, the Earth's spin axis could, in theory, vary quite a bit. And so, if we had never had a moon at all, then we wouldn't miss the moon because that stabilizing effect only works for certain frequencies of Earth's rotation. So after Earth formed, it was probably spinning a lot faster. If it was spinning fast enough, then the moon wouldn't have done anything anyway, right? But still, the moon in the sky is awesome. We think of it as a good thing for life, at least philosophically. Is it really that great for life? No one really knows. But where I'm going with this is the new study that I'm doing is trying to actually take the opposite point of view and argue that the moon's bad for life. And it's not terrible for life in the present day solar system, but it's bad in case things go a little bit wrong. It's like having a super dumb friend who's going to like do the really wrong thing with you in an awkward situation. It's just going to make it a lot worse, right? And so tough situation, moon makes it worse. And so basically what happens is I found this during the simulations that I did for that project of zooming a star by. I did a subset of simulations where instead of just glomming the Earth and moon together, which is what's always done in these kind of simulations, because if you want to actually resolve the moon going around the Earth, it takes a lot longer. But a collaborator of mine was like, let's do this. He was really excited about it. And so I figured it out. And I did a few hundred runs with the Earth and the moon as actually separate particles. And to my surprise, the moon fell on the Earth a lot. And so it didn't just fall on the Earth randomly. It's not like that caused the solar system to go unstable. But when the solar system became a little bit unstable and planets' orbits were kind of maybe Mercury is the planet that's most often goes crazy, or Mars, they get kicked around, they get scattered off of the Earth, something like that. And then the moon falls on the Earth. Right? It's not good. And so basically, the punchline is if things kind of go a little bit haywire in the solar system, the moon is a really bad friend to have around. It's like the dumb friend who's gonna, I don't know, shoot you in the foot or something like that. It's like a really bad idea to have the moon around. And the reason is really simple to understand, like intuitively, right? You can imagine as the Earth is zooming around in space, it's a target of a certain size, the size of the Earth, right? So anything really bad is if something hits the Earth. But, the moon orbits the Earth at about 60 Earth radii. And so there's another target, which is the size of the whole Earth-Moon system that's bigger by, 60 squared. It's like 3,000 or 4,000 times bigger, the size of this target. So it's a much bigger bullseye. And if a planet or something else really massive goes, close to that bullseye, it can mess with the Earth-Moon system. And what does that mean? Sometimes it means the moon just gets stripped away and goes off. But sometimes, a decent amount of the time, the moon falls on the Earth and kills us all because it's pretty massive. And so this new study is just it's kind of a philosophical paper, just arguing with some of these simulations to back it up that the moon is not our best friend. It's not good to have around.
What happens to the Earth if the moon leaves?
Good question. Probably nothing. Probably the Earth doesn't really care that much about the moon being there. We have the tides, right? Tides are nice. But the tides come from the sun. Tides from the sun are about half as strong as tides from the moon anyway. So we'd still have tides, they'd just be a little bit weaker. Otherwise, we'd miss it in the sky. It's really pretty, right? But it doesn't functionally do much for us.
Interesting. So. Isn't it huge? Like, I'm going to sound stupid if this is wrong. Isn't the moon like a quarter of Earth's size?
It's pretty far away though, and that gravity falls off the inverse square.
It's crazy to me that something that's so big and so close, relatively speaking, would just have no effect if it was to just get lost.
Oh, I mean, it's not none. It deforms the Earth, and so there's tides. There's solid body tides. The whole like rocks on the Earth deform by, I think it's a meter or so every day. They squish up and down. And the water does that, the same thing with a much bigger amplitude.
So does the Earth
yeah, I mean,
cool a lot faster then?
oh, that's a good question. I don't know. I know that there is a heat generated within the Earth due to tides from the moon. It's not that high compared to other sources, but it probably has some effect on the cooling. Yeah.
Yeah,
Well,
like I
suppose
wonder on the order of the age of the solar system, because do we have a sense for why Mars is so cold?
it is because it's small. So there are models showing that Mars could have, in principle, had liquid water on its surface back in the day while it still had a thicker atmosphere. And why did it lose it? And everything is related to its cooling off, which is related to its size. So that's possible. Yeah.
Also doesn't have that nice magnetic field that we have. I wonder if that the moon has any like if keeping the swirling sub-crust magma stuff in order is in some sense, in some part, due to the moon's orbit around us.
This is quickly becoming computationally intractable.
Oh yeah, I can just say random things. We'll see. I'm not going to compute this, but I mean, the Earth's magnetic field comes from the outer core, the part that's liquid, and that part I don't think is affected by the moon at all. It's or at least to a minimal degree. I'm saying that as a blanket statement that I cannot really defend at all, but I don't think that's the case.
This is really it's very whimsical research. I feel is this unusual in the planetary sciences? Because
yeah, it seems incredible that you're able to get funding to play with these ideas in such a just curiosity-driven manner.
Yeah, I don't mean that as a derogatory statement. I think that science really flourishes when it is whimsical in this way, where people are like, "Well, what if?" And I feel like that's rare.
Over the past many years, I've shaped the kind of research I do to deliberately do those kind of questions, and it's because I enjoy it. And I think I don't know if from people I've talked to, I think everyone has these sort of cycles. I personally, have cycles of motivation that go up and down quite a bit. And so on a monthly basis, I'm like, I should quit and go do something else. And what keeps me going is little things that interested the younger me that maybe ever want to be a scientist in the first place. And those are these kind of whimsical things. And so I deliberately avoid too many projects that are kind of, let's hammer out exactly the details of this or that. I've done plenty of studies like that, right? I still participate in plenty of those. I don't generally lead those anymore, but those are important and interesting, but they don't kind of keep me going. And so the things that keep me going are these little side things. They're these kind of crazy ideas that are fun to test. And when I talk to other people about them, it stimulates cool ideas in them too. And they often end up being ideas that are, strangely applicable to the history of the solar system or something else. Right? They start off going in a random direction, but they usually come back and have some relevance in something that's relatively concrete. And so I kind of need them to keep going. Without those, pretty quickly, I'm like, I gotta do something else. And I haven't quit yet. So I've been around for a while, which is, I guess I have enough of these things going. But I also have the kind of job where I can do that. So the kind of job I have is I'm a French civil servant. And so it's like a NASA job, except it's on hard money. And so I'm basically was hired to do whatever research I want within astronomy, right? I was not hired to go and, write books about puppies or anything. Not that I have anything against puppies or books like that. I was hired to do astronomy research. And so I still do astronomy research, but I give myself permission to explore whatever I think is interesting at the moment. And
you think that's just more possible in that funding superstructure compared to the United States?
Oh yeah, definitely. So I think it's more possible there. I don't think there's anything that's really stopping it from happening in the US. It's hard to do that kind of thing as a funded project, right? And so if I was going to try to get this moon idea funded and get a grant for it, well, what would I do? I'd have to do part of the project first to show that, like, a proof of concept, it has some interest. Then I'd have to show that it's relevant to something related to NASA's goals,
Hmm.
which it is, in terms of the search for life around other stars. This is a key thing. Do we need to look for another moon? There's a bunch of people who would say, yeah, we need to find, a rocky planet with another moon. That's a key check, box to check on the list of habitability. And I'd be saying the exact opposite. So I can argue that as something that's relevant to that. And then I have to go and write a grant and get it funded and hire someone to do the actual research while I wrote another grant. Right? That's kind of how it works. And so I can kind of skip all of that with the kind of job I have, where I can just kind of ask these questions and go and explore them right away.
Mm.
And I really appreciate that. I do still write grants and get students and postdocs to work on various things. But the part that I enjoy the most is coming up with the kind of crazy ideas.
If you were to leave science, what would you do? Like when you get into that slump and you fantasize about what could be.
I mean, realistically, I think about it, like I said, pretty often. And so I would have to, the downside of the kind of job I have is it does not pay well. And so if I were to get another job, I'd have to make enough money. I'd probably go find some tech company and work for them or something.
But in an
That's
ideal world where there
the
was no, let's say that there's no financial burden that hangs over your head, what would you do?
I always wanted to be a writer when I was a kid. And so now I would probably spend a lot more time and do the kind of the things I do for a job, but just do the blogging part and just do the crazy ideas part and skip the the more common working on the details of this issue here and all the administration part. So
It's-
the
it-
kind of the fun stuff.
Yeah, I'd love to see you paired up with more sci-fi writers. I feel like we could get some really interesting content together.
Well, not even just paired up
Yeah,
with.
so
Oh, go ahead.
I do some of that. I've had a bunch of science fiction writers contact me for helping them come up with settings for their book or whatnot. And on a whim, I wrote a book of astronomy poems a few years ago. This kind of thing.
Does that fit under your mandate by the French civil service, where you're still working on astronomy if you're writing sci-fi books? I feel like you could probably spin that. You might have. Do you have to write them in French?
No, I did not write them in French. No, but I'm going to say, yeah, I think it's probably okay.
Because I think that there is some aspect of astronomy that has to do with, like Shiloh said, it's this project of inspiring people to go to the stars and to think about the long-term well-being of the planet. And so if you've managed to push it to this degree of contemplation about what if, it seems like you could probably push it one step farther and actually just start writing sci-fi and still be within the
Yeah.
bounds of, or is there like a demand, is there the same sort of publisher perish demand where it's like you have to be publishing academic papers in the position that you have?
Oh, probably. I published quite plenty of papers. I'm not terribly worried about that. I think, I'd have to prove that I'm publishing at least a few papers a year, but I collaborate with a bunch of people, and so there's always papers in the pipeline. But yeah, I think I could definitely like argue that this kind of exploratory thing, and I do a decent amount of outreach also given public talks and stuff like that. And that's definitely part of the job, right? So that kind of thing I do quite a bit, and it's fun because people are interested in it. Everyone's interested in talking about space, and everyone's interested in kind of crazy ideas about space, which is fun. And there's practical considerations too. And so I always tell them if they really want to go become an astronomer, here in France, I tell them they need to learn English first, and then physics and math and computer science and stuff. But yeah, it's fun. So it's that kind of thing is a fun way to inspire kids, and they always love the crazy ideas, of course.
If you were to write a sci-fi book, do you have books laid out and plots kind of in the back drawer, or is it something that is tentative?
I've had lots of these. So when I write about on my blog, I often come up with kind of a setting, and then for fun, I'll write like a few paragraph little science fiction story. And so I've gone through a bunch of these kind of like in very, very simple terms. And so the first one that I had that I still like the idea of is, imagining, a situation where, on a rocky planet in a system, the astronomer types, observe in time, they somehow basically figure out that their own planetary system is going to go unstable. They see like that the motions of the Jupiters in their system are such that in a certain amount of time, they're going to have one of these events, these giant dynamical instabilities that we know really happen all the time. And it's going to destroy their rocky planet. And so how do they handle that? Because they still have a few generations to go. How do they handle it? What do they do about it? How do people freak out? These kind of things. So that was kind of the first idea I had, which I still think would be a fun one to write.
Yeah, definitely.
And yeah, I really appreciate your open-mindedness and entertaining our kind of ludicrous ideas. And because it's often you talk to people and they're just like, no, that's so unlikely that we shouldn't even talk about it. And I think I don't know, it's just there's something about the fact that we're the only life forms that we know about in this whole sea of the night sky, essentially, that makes me think that sometimes the unlikely is the case. And I think it's really worth thinking about, especially when we're talking super long-term, billions and billions of years and huge, unimaginable swaths of space.
Yeah, I'm like, because if you sat down to calculate the probability of this moment,
like us having this Zoom conversation, it's unimaginable. Like no one would ever predict this is going to happen.
This is so funny. When I give talks about, I often give talks about how the solar system formed, and I used to say it was this one mechanism, and now I say there's many different kind of key mechanisms, and we don't know if it's this one or that one or that one. And people often ask the question of like, that seems awfully specific. Can that really have happened? And then I do some similar thing to what you're saying right there. I would say like, imagine a person, what are the key events that shaped that person? What family they were born into, where they went to college, their first love, there are kind of a few things that were kind of key shaping events that are similar for everyone, but they're also different for everyone because everyone has a different experience there. And the branching of like what kind of person you are depends on those things. And so what are the odds of someone having the exact experience you had? Is zero, right? Just like you're saying, but it happened. To try to see when you're explaining even a planetary system, it's like an individual. And there's certain branches that were followed to end up where it's at now. And, the probability comes into play because something that can't happen cannot have led you to where you are today. But it's a tricky thing to evaluate the probability of these different branches. And the cool thing now in terms of the research part is we got our solar system, we got thousands of other systems. And so it's more of a population thing. It's not like we're looking at one individual anymore. So you can kind of zoom out at that also.
I think like the population selection dynamics too, if you bring just evolutionary theory of biology and start thinking about like the heavenly bodies too, or whatever you want to call them, like all these celestial objects, it's like you're only looking at what survived to some extent too. So you kind of miss out on all of the failed experiments. And I don't know, it seems like the rare can become common at some big enough scale.
Well, yeah, I mean, like hot Jupiters, very simple sense. Hot Jupiters were the first 10 or 20 exoplanets were hot Jupiters. Those are very rare planets. They're just the easiest to find. There's all these filters between what's going on and what we get to see. And so there's what happens, what survives, and what we can see. There's this old kind of, story that they tell all astronomy grad students that maybe you've heard before, where there's some guy who lost his keys in the dark and he's looking under a streetlight and someone comes up and it's like, oh, what's going on? He's like, I lost my keys over there by my car. And the person's like, well, why are you looking here? And it's like, this is where I can see, this kind of thing. And so it's a dumb thing, but just kind of illustrate the biases we have in terms of what information we can actually get. And in astronomy, there's tons of these biases all over the place, but people have been studying them and trying to quantify them, forever. So we try to take that into account anyway.
Yeah, absolutely.
As long as we can keep those in mind, I think we can be healthy enough when we come up with mechanisms to be like, hey, this is the best thing we can come up with, but in some sense it's limited by all of these other conditions that have given us the ability to even see what we're looking at. And, as long as we keep that humility, which I think you inspire a great deal of that, and it's yeah.
Oh, thanks.
It's good to see that. There's too often that I talk to people who are at the cutting edge who are 100% convinced that there's one story possible in any given, thing that occurred billions of years ago. And it's always, I don't know, it's a little disturbing because it might be very, very likely, but you still got to keep your mind open that there might be something you don't know.
This is a tricky thing. So I've spent a lot of time thinking about this. And so having very strong beliefs that you'll never change is not useful, right? Because you'll never change it. Jumping from, flapping in the wind to any new tiny data point, I don't think is that useful either, because then you're always changing your mind and you're never going deep enough. So what's the balance? I think the balance is what I see among some people, which is, holding on to your beliefs pretty firmly, but still listening to everything else and having an open mind. So at some point, it's like, what's the critical mass of arguments that go against your idea or evidence that goes against your idea before you switch, right? You don't want it to be a tiny amount because then you're just giving up right away. And who knows, that data point might be a 5 sigma data point, might be nonsense. Right? That happens all the time. Like the free-floating planets that were way too abundant was not true. But everyone thought it was for a few years because that was what was measured. And so you want to hold on strongly enough, right? But you don't want to hold on when it's really clear that that's, there's enough evidence to really shoot down your argument. And I don't know of a way to use numbers for this. You can always do it in some way, because if it's a very specific fit, then you can use some statistic for it, like, p-values, or use Bayes' theorem or this kind of thing. But if it's just a kind of a conceptual model, then it's up to the individual, I think, to manage this internally, where it's like, I'm going with this idea. I believe this. I'll listen to your other ideas. And it's only once you've shot down my idea to some level of rigor that I'll be like, okay, I got to back off on that one and switch. And it's really hard to do that. And I think this is why so many old scientists end up with their own pet crazy ideas, because they've never been able to, they basically set too high a threshold for backing off. And they'll tell you that they're open-minded, that they're willing to change their idea. All you have to do is find that one missing proof that that's the case, right? And so exactly how deep that should be is a tricky question. And I have some experience personally in seeing it in other people, but it's hard to put a number on.
Well, there's a great weight of, what makes sense conceptually versus quantitatively. Because I think that oftentimes the ability to express oneself in mathematics lags behind the ability to imagine something as just bodies moving and interacting. And certainly at some point you have to put it through the paces of, does this compute? But sometimes the ability to compute it is difficult, or somebody hasn't worked out the math yet, or you don't have the right equations for it. And so there is this phase of just being able to look out onto the world and to ask the question of, well, what could it be? And
it's like all these quantitative arguments can always be modified too by introducing new elements, new variables, like, well, what if there's a moon on the sky all of a sudden? Or, what if you just throw in one more piece of qualitative information that you need to parameterize, and you can modify a lot of these quantitative arguments.
Yeah, and I guess that the way that I would bin that is to say that it's worth remaining sufficiently open-minded that you can accept the theories of today are not going to be the theories of 1,000 years from now. Because I don't think that we have a single theory from 1,000 years ago that we look at and we're like, yeah, that's definitely the right case. Because honestly, it's a metaphysical question. Like, if you look at the history of thought over the course of the Middle Ages, so like the ancient Greeks basically came up with all of these ideas about substantial forms and Platonism, and out there was the realm of the ideal, and here's the terrestrial realm, and that was basically it. Like, that fit really nicely with medieval doctrines of the church, and so that was the only way that you could model anything for 1,000 years. And I've been thinking about it a lot, and I'm like, what if that's just what happens? Like, what if we get captured by a certain set of metaphysical principles, and they're so foundational that that's just the water that we breathe and we cannot see through them until enough people start to come around where they're like, hey, I don't know that this holds. Because literally there was a guy in ancient Greece, Democritus, who came up with this idea of the indestructible atom. But Aristotle was the tutor to Alexander the Great. He was one of the most famous philosophers of the time. He was associated with Plato. His idea of forms and the Platonic kind of Pythagorean mysticism that preceded them was very much embodied in his work. And so Democritus faded. And the church didn't like any of the ideas because they proposed that there was no possibility for this immortal soul. And it took until I think people started to translate the poems and to start to bring them back around in the 1300s. And then even after that, it still took another 200 to 300 years for people to start to really come back around to this idea of atomics. And Descartes is basically famous because he was one of the first people to be like, no, I think Aristotle's bullshit. And that took so long. That was the
That's amazing.
1600s.
That's super interesting. Yeah.
And I'm
Wow.
like, what is that metaphysical morass that we're in right now? What is the thing that we cannot see? What if we're in the equivalent of the 1200s?
That's a really good question. I don't know. I don't have a great answer for you. That's because all the things that come to mind are so much, they're not deep enough, right? I can describe these different ideas related to how the solar system formed, but that's kind of not a very deep thing. It's really I feel like what you're talking about is really kind of a very, ground level thing where everything else is built on top of that. And so it's not really did this model or that model or that model explain the early solar system? It's more like, can we ever understand what happened there? And is there, a universal process at all that does that? Or, how much are stars and planets really individual, like I was describing? And how much are they really kind of a sea of very similar things? I think that's the kind of level where we all assume, at least in the field, we all kind of assume that yes, we're going to be able to figure this out, that it matters, right? It matters enough to put our time into it. And that, there's something also just the kind of, even if everything is individual and has a specific story, we can get at some population level, model or understanding what's going on. And so those kind of beliefs, I think, are key to keeping the field of planet formation afloat. And it is afloat and doing fine. But if people didn't believe those things, it would go away.
Sometimes people's beliefs change radically too, right? With biology, most people used to think all the different animals had their own lineages essentially until not that long ago. And nowadays, pretty much everyone understands that all the animals have an origin point, which is really interesting. They're all sort of doing the same thing. They're just evolved. They've been subject to different pressures and different interspecies dynamics, and you get a bunch of very different looking creatures. And I wonder how much that kind of evolutionary thinking will play into the future of planetary sciences.
That is interesting. There's one other thing that comes to mind in terms of even a bigger question of that's kind of behind a lot of this stuff, which is the search for, life on other planets. There's kind of, you guys have probably heard of the Drake equation and everything of, how to kind of figure out the odds or kind of, in simple terms, the odds that stars will have life on, will have planets that are capable to have life on them and may even have life and life that could communicate and so on. Behind all of that activity and all the push to search for biosignatures or life on other planets, behind all of that is kind of the inherent assumption that there are aliens out there, right? This is behind all the science fiction stories that we love and everything. And it's not a given. This is one of these things that we don't want. I think most people, the vast majority of people, are really rooting for there to be life all over the place and aliens and everything. But when we're in the one example that we know, on the one planet that we know has life, There's no given that those other planets actually have life, that it is elsewhere. There's lots of arguments to be made that, that we know there's tons of rocky planets out there. There's so many that most stars have them. Plenty of them are going to have water. Anywhere there's water on Earth, there's life. So there's got to be water on those planets, right? Well, not necessarily, right? And so I think that's another one of those things where there's this guy, David Kipping, who makes this point really, really elegantly, basically just arguing that everyone wants the answer to be that there's life out there, but there might not be. And we really need to keep that in mind and not to just jump on the bandwagon of what we want to be true rather than just seeing what's out there.
It's a really good point. It creates.
I'm definitely one of those people. I really want there to be. But yeah, if you think about just if it's been 300 years since we've been a technological civilization, we've been like making electronic things for what, a little more than 100 years. It's like, and God knows how long we'll be able to persist. I mean, I hope we'll keep going forever, but
probably won't.
I mean, if you think about the odds of a technological civilization persisting for more than a few hundred years, it's like that'd just be a blink of an eye. It would just, maybe it happened, maybe it's gone, maybe it happens all the time and disappears immediately.
But beyond even the blink of an eye. Oh, go ahead.
Oh, no, I was going to say, yeah, I mean, totally. There's all these arguments. There's so many planets out there. Even if only one out of a billion planets like ours ends up, forming, having a life start on it, it should still be out there. But that's still saying that at least one out of a billion has to do it. And so it's not necessarily true that just because it happened here, it has to happen elsewhere.
Especially in our time period.
Mm.
Oh, yeah, exactly.
At this moment.
Detecting it too. Yeah.
I actually have perhaps the unreasonable belief that there is life everywhere, because I think that we have a tendency of looking at life as what cells do, rather than life being some process that precedes cells, which is some thermodynamic organization of matter in a crystalline form that then eventually gets to a functional place where it can form cells and then become very effective. And so I can imagine really easily that, you dig down far enough inside of Mars and you find something that's like proto-cells, something where you have these, because these are really, really difficult things to actually find and study, right? Like there's...
For sure. It's a cool, yeah, I like your point of view is really interesting though. Sorry.
There was this, if you're interested in it, there's this guy, his name is Tullis Onstad. He died a couple years ago and he wrote a book called Deep Life, which is a nonfiction book just about his work on like geomicrobiology. He was a geologist and he got really, really interested in pulling rock cores out of the earth and looking to see what was the deepest life you can find. And you can find life that's miles deep. They were finding these crazy worms in gold mines in South Africa, 2.5 miles down, that lived in crazy acidic and saline conditions, and bacteria in all these places where they wouldn't expect it. And I wish so badly that he was alive, because there's a couple times in his book where he talks about the fact that they would pull up water from these deep boreholes that they would make miles underground. And he's like, it appeared to be that it was on the cusp of life. Like it had all the stuff that you would expect from life, but it was so far down that and it was so old that it couldn't have filtered through from other pieces of digested stuff. And so you can tell that he has this like borderline thought of like, I think that it might actually be coming from the earth, but he was so careful of a scientist that he never came on record to say it. But I think that the rarity is a planet where conditions are good enough to be able to allow that to proceed to the place where we are today, doing the insane things that we do. And so it makes our project so much more valuable. Not like this podcast, but just like the human project.
Yeah, totally. If this is really the one in the bazillion planet with life, it's a shame when the egos of some people in power put the survival of the whole species at risk. It's crazy.
And it's just on a daily level. Like, think of how significant it is if you're raised with the knowledge that this is it. Like, the humans are the ones that are responsible for making sure that everything that was ever made on this planet, from the like smallest bacteria to the most complex opera, doesn't just get digested by the motion of the spheres. Like, that's quite the
Really
obligation to
cool.
the universe.
Seriously, no pressure. No, but I like that. It's really deep. I really appreciate it.
I mean, it's really cool that this is what you spend your time just wondering about, and the probability of survival versus escape, and the level of friendliness of the moon and how good it is for us, and all of these other questions. It's really, I love that this work is out there.
Oh, thank you. I appreciate that.
You have any closing thoughts?
No, I think it's also really informative about the structure of funding in academia, and a lot of people, a lot of academics come on our show and complain about how difficult it is for them to study the things they really care about because they have to cloak it under these technological guises. And
So they should all become French civil servants?
I don't know. I mean, the UC system, the California system, was pretty badass when it was state funded. I'm generally not like a huge fan of the state running everything, but it seems like when it comes to university, it does perhaps allow for a lot of innovation, and so it's a really interesting case that you present here with your own work. Gives me something to think about.
Yeah, I'm definitely a rarity in astronomy land too. But this kind of job is there's plenty of them in France. In the States, jobs that have enough freedom to explore things, they exist, right? They're out there. There's a few here and there. But the majority of people are kind of always following a process of getting the grants and everything and doing more standard stuff, which is exciting and fun too, right? I have nothing against it. That's how a lot of advances get made, just kind of on that normal path. Just personally, like I said, for my own kind of the spirit part of me that made me want to do this in the first place, it doesn't excite me to do that in kind of that fashion. And so I do it to some degree, but I don't spend all my time doing it anyway.
There's a lot of evidence about the stagnation of innovation particularly in Western science, and just there's a lot of different explanations you could take for that, but it does seem like people don't have as much time to play as they perhaps did in the heyday of science when everybody was a rich baron essentially, and so I'm always looking for ways to pollinate just sort of fertilize the atmosphere, scientific atmosphere. But
It
yeah.
seems like having a podcast like yours must be fun for you to be able to talk to people and throw ideas all over the place. It must be. I'm guessing it's a pretty enriching thing to be able to do that.
I mean, a lot of what we're doing is throwing other people's ideas at each other. Like, we're taking people's ideas and throwing them against one another, because a lot of these people would never be in the same room together. And so we're kind of like the bee that's just bringing the ideas from place to place, the little pollens. And,
I mean, the goal is to build up a library of these theories and to put people in contact who are curious about the same things. And in the long haul future, I would really love for it to be a sufficiently powerful organization that can actually fund people doing research, and to fund projects where people get to play and they combine their interests and are actually able to be free of these granting agency and oversight requests. And so this is like the first slow steps in that direction.
Yeah, we really want to bring people together. We're having our first conference this year, so
next year,
next year,
exciting.
yeah, 2024. Which will be pretty tiny, but I imagine like 10, 20 years from now, we could actually get some really interesting people in the room together.
Yeah, do you come
That's really cool.
stateside often?
I come from time to time. We were there a couple weeks ago. My family lives in Colorado, and my mom's not doing well, so we were out there visiting. But otherwise, I before COVID anyway, we'd come to the States at least once a year, and so I usually go to a conference or two in the States every year. So I'm around.
We're organizing it for April of next year, April 7th and 8th, to coincide with the eclipse, and it's going to be in Austin.
Oh, that's cool. That's cool. I'm going to a conference in Rochester that's also designed to be for the eclipse at the same time.
All right, very nice.
Interesting. Yeah.
We thought about doing upstate New York, but we have a friend that lives up there, and he's like, "You're not going to be able to see anything in April." He's like, super cloudy. And so
A
we
friend of mine
aired.
did the statistics on the weather, and he said in upstate New York there was something like a 40% chance, and as you move further south, it got up to like 60%, something like that.
Yeah,
So
exactly. And so we settled on Austin because we were like, okay, this is like close enough to the upper bounds of success for that. Because we had
that's good.
the recent partial eclipse here, and we're in Southern Oregon, and we did not see it. Too cloudy.
Yeah, just
Oh no, bad weather.
It just rains. It rains.
just overcast. Yeah, a few towns down, they saw it perfectly. So we did not luck out. So we're going to the desert. We're
Yep.
gonna see it this time. Yeah.
Nice.
But yeah, we should catch up down the road again. Your work is really interesting, and you're clearly thinking about a lot of super, just fantastical things. And we talked to Nate Kaib, who's one of your collaborators, who just had extraordinary things to say about you and how much he loved working with you.
He's great. Nate's great. That project I was talking about the stars zooming by is with Nate, and so is the moon one.
Oh, very nice.
So Nate, I have about 2 or 3 collaborators who are my favorites, and Nate is at the top of the list. He's fantastic. So
Who are the
that's
other
really cool
ones?
to talk to you guys. Well, I have a friend, Andre Isidoro. Do you want me to give you their names?
Yeah, because we're gonna follow up.
Oh, sure. So Andre Isidoro is great. He's at Rice in Houston.
Mm.
And then after that, they're kind of my 2 go-to guys that we collaborate all the time. And then I have a bunch of other collaborators who are also great all over. They're mostly in the US, my collaborators. So a bunch at NASA Goddard and elsewhere.
It's good to have the worker bees, you know, the 70-hour work week grind set mindset.
Oh, yeah.
All right, sir. Well, yeah, thanks for giving us so much of your time, and it's just
It was
been
fun. It was a lot of fun talking to you about all this crazy stuff, and I appreciate your crazy questions. I think they're great. So some of them I didn't know how to answer because I don't know what would be different if the universe was older, but it's worth asking.
Hopefully we can figure it out, and we will let you know when we do.
maybe 1,000 years from now.
Please do. Yeah, exactly.
Excellent. Well, have a good rest of your night.
Cool, and have a good day.
Oh, and then hey, hold on, before you go, tell people where to find you.
Oh, okay. I guess the main place to find me is my blog, which is planetplanet.net. Otherwise, I'm on Twitter or X. I'm @Raymond_astro.
Excellent. All right, well, hopefully people will find you there. Thank you so much, Sean.
Cool. Oh, it was a pleasure. Thank you.
All right, take care.
Bye, everybody.